So you guys can see this is kind of combined. It's something you want to know for A2, but it's much more detailed for A3. So this will be applicable to both. And it's drive shafts and CV axles. It's a little bit more on drive shafts. Drive shafts tend to be a little more technical, but CV axles are in here too. So here you go, right off the bat. The drive shaft, why we have it. Well, if you look, it's kind of from bottom to top over here. We've got the engine in the front, which goes to the transmission, which in this case goes to a transfer case because it's four-wheel drive. But if it was two-wheel drive, the drive shaft would just go straight through where the transfer case is and go in the back of the transmission. So if it's a rear-wheel drive, the transmission doesn't have the axle, it doesn't have the final drive or the differential. So that goes directly back to the actual differential. So the drive shaft really needs to transmit the power from the back of the transmission to the rear axle, assuming it's rear wheel drive. If it's four-wheel drive, it's still going to have a rear drive shaft to transmit to the rear axle, but then it'll also have a transfer case, which will bump it over and send it to the front diff. That's why it's a little more manual transmission oriented, because manual transmission ASE includes four-wheel drive. But with that being said, it propels the vehicle. For that reason, a lot of times they will call it a propeller shaft. So if you hear drive shaft or propeller shaft, it could be talking about the same part. Sometimes they'll also call the CV axles propeller shafts or drive shafts. Mostly going to be drive shafts. Sometimes they're going to be half shafts. So there's a lot of terminology here that you'll need to be familiar with. So as we're talking about this drive shaft, just keep that in mind. And then as we get further in, the reason that we really need to cover drive shafts is you may not have this transfer case or this back of the transmission in perfect alignment with the rear axle, like side to side. So we have universal joints or U joints that can basically kind of function like a swivel on your extension to get around the corner a little bit. But from left to right is not so much the big deal. It's really actually up and down. So we're going to look at this from a few different angles, and then you'll understand why the drive shaft has to have these universal joints. And the problem with the universal joints is they're great, but they're a little picky with regard to the angles that they like to operate at. Okay, so continuing. If you look at the drive shaft, keep in mind, as that rear axle goes up and down, that's going to lessen the distance from the rear axle center line to the back of the transmission. So this drive shaft has to go up and down, which means it has to get shorter and longer, and it has to be able to flex. So we've got a U joint here and a U joint here. And as we get into some of this discussion, the angles are very critical here. It's mostly actually the angle of the pinion and the angle of the transmission. So when you start doing vehicle modifications, that's when you may run into some problems here. If you modify it, you really need to know what your new angles are, and there's specifications on that, but you generally won't find them in the service manual, simply because, let's say this is a Tacoma. The service manual doesn't write specifications for people to be able to mod the vehicle. They write the specifications for people to be able to repair the stock factory OEM vehicle. Makes sense? They're not really trying to support the aftermarket. But some of the aftermarket companies will put out some pretty good information. So a lot of what we're about to talk about is more applicable to people doing lifts and lowering and modifications and building custom drivetrain. With that being said, because we're really trying to prep for the ASE, we're going to cover it to what you need to know for the ASE, but probably more too. And I think if you understand more it'll make it even easier to really understand those ASE questions that are related to drive shaft issues, particularly vibrations. Vibrations can have a lot to do with the drive shaft. All right, so continuing, remember the drive shaft's going to transmit the torque, and as it spins, we got a problem right here. It's talking about the drive shaft is going to increase and decrease velocity at that universal joint every 90 degrees. Keep that in your mind. We use the U-joints because we need to accommodate angles. Left to right, a little bit of angle, but up and down, it can be actually kind of a lot of angle depending on where that rear axle's at, where the suspension is. The suspension in fully extended or fully compressed. Can make sense. And then on some vehicles, they'll actually use drive shafts where they eliminate the U joint, the universal joint, and they'll use a CV joint. And that's a really good option, but it's more money. Universal joints are cheap. CV joints really are not cheap. But we're going to compare both of these two. And then there's this thing we're going to talk about, Hooke's joint theory. You really just need to know it as a theory. I'm not ever going to ask you to, give a lesson on Hooke's joint theory. The ASE is never going to say, describe Hooke's joint theory. A customer that's sane is not going to ask you to describe Hooke's joint theory. But if you understand it, you understand why we need to mark our drive shaft before we disassemble U-joints, because if you put them out of phase, we can cause some vibration. And also, if we start changing our suspension, why we would need to keep in mind some of these angles. From the factory, these angles are in spec. After your mods, they may be out of spec. The reason that's a problem is Hooke's joint theory, right? So when we talk about this, we're going to be really discussing a universal joint. So this is the universal joint. It's basically, they'll call this the cross. You can see it's like a cross. And then these will be the caps. And then within the caps, there's needle bearings, right? And then that universal joint will be installed in the drive shaft right here. There's a joint here and there's a joint here. This one actually has a little bit more going on. This one has a slip yoke built into the drive shaft, so that's nice. This one also uses companion flanges, so there is no ability to slip in and out of the transmission. The drive shaft is bolted up solid with companion flanges, which means the drive shaft itself has to telescope, if you will. And then there's a big yellow line all the way down this. This is kind of excessive, but it's more for visual. If we're going to disassemble this drive shaft, you have to make sure that you put it together exactly how it came apart. So we mark this yoke, we mark the whole shaft, which that's why I'm saying it's excessive. Like you could just mark the end, but sure, we'll draw it out. Mark it. And then we're going to mark this yoke. So when you put it together, if you accidentally had this yoke flipped over or out of phase, that's when you'd get this companion flange would be flipped and the drive shaft would no longer be either balanced, or if it's out of phase, you're going to be affecting the Hooke's joint theory aspect. Okay, so when we get in there, this is just kind of describing when we use those universal joints, it's going to induce all this Hooke's joint theory. It's going to talk about the angular velocity, which increases and decreases. And we got that charted out for you. And then just a preview, we're going to talk about a double cardan, and we're also going to talk about CV, constant velocity joints. So if you did the correct assignment, you would have watched a video. So you should be semi-familiar on this. A lot of this is hard to explain with words. Pictures help. Animations are infinitely better. I don't have the ability to make animations, at least not yet. Maybe someday. All right, so here's going to be your drive shaft. Let's just say you're starting at 0, and then you're going to turn about 45, and then you're going to turn 90, right? 45 and 90. So right here we have an out. Let me look at this. The output shafts of the transmission is constant. All right, so it's 1,000 RPMs at the output shaft of the transmission, which becomes the input to the drive shaft. Everybody clear? So like basically, we grab the drive shaft and we start spinning at 1,000 RPMs. And this may not necessarily be to scale, but it's a representation of the Hooke's joint theory. So if we're inputting 1,000 RPMs, when this universal joint is like straight up and down, let's say at the 0 degrees, it's actually going slow. And then as we turn it 45, look, it speeds up. And as we get it to 90 degrees, it's reaching its maximum speed. In this example, 1,300 RPMs. And then once it crosses 90, Andres, I'll come back to you. Once it crosses past 90, it's going to actually start to slow down at 135. And then it's going to reach its slowest speed at 180. So that would be like a half a rotation, right? And then when it reaches 180, it's again going to start to speed up. At 225, it's speeding up still. At 270, it's reached its maximum speed again. And then on the way back toward a full revolution, it starts to slow back down and slow back down. And then by the time it's back to that 360 rotation, which is really zero, it's reached its minimum speed again. So if we were to look at it like a clock, it'd be 12 o'clock is slow, 1 o'clock is speeding up, 2 o'clock is speeding up, 3 o'clock has reached its full peak, 4 o'clock is slowing down, 5 o'clock is slowing down, 6 o'clock has reached its full slowest, 7 o'clock it's speeding up, 8 o'clock it's speeding up, 9 o'clock it's reached its full fastest again, and then 10 o'clock it's slowing down, 11 o'clock it's slowing down, and then at midnight it's reached its full slowest again. So it's constantly oscillating in speed. In 1 360, it's done actually 2 cycles. In a 90, it's gone from the slowest to the fastest. Then it goes to the slowest and to the fastest again. Okay, Andres, go ahead.
Could worn out U joints cause the vibration in the drive shaft?
Yes, but you're a little ahead of me, so slow it down, baby.
For sure, for sure.
Good. So when we talk about this, this is just the natural function of, unfortunately, the universal joint. And I don't know the guy's first name. Some guy named Hook figured this out. He figured out these speeds can be measured. Okay, so if we were to apply this, and this upper one is with a drive shaft with a output shaft at 30-degree angle. Okay, so we've got a really steep inclination here. That's going to make this worse from 700 to 1,300. We can minimize that by leveling these out at 10 degrees, and it's going to have less, right? Acceleration, deceleration, acceleration, deceleration, but it's only swinging a couple hundred RPM, whereas this one was from 700 to 1,300, right? So 600 RPMs. So depending on the inclination, in other words, the angle of your drive shaft, it's going to make it more severe or less severe. But I'd like to clarify that a little bit. It's going to take this picture. So when we're talking about those speed changes, that would really be like this input shaft is 1,000, and this was the one, the output, which is kind of like the actual tube of the drive shaft, you can see right here, would be oscillating in speed. All right. So if your transmission's putting out 1,000 RPMs, that becomes the input of 1,000 to your drive shaft. And then it's basically going to oscillate in speed. It's going to go up maybe as high as 1,300. It's going to drop down to 700. It's going to speed up to 1,300. It's going to drop down to 700. It's right. So this is staying constant at 1,000. The actual speed of this sucker is fast, slow, fast, slow, fast, slow. Even in one revolution, it starts slow, it goes fast, it goes slow, it goes fast, it goes back to slow. So it's changing a lot. Now, if you look, if this is speeding up and slowing down, don't you think that would cause a crazy vibration? Like kind of what Andres is already getting at. So it's in its natural state, this drive shaft vibrates. But this is what we do that's pretty ingenious. When this one's at 1,000, it's actually starting to speed this up. But when it speeds up the drive shaft on the input, it slows the drive shaft down on the output. It's kind of crazy to think about. So if you look at this, as long as this angle is the same as this angle, it will slow it down on one end and speed it up on the other end equal but opposite. So you get 1,000 RPMs in and 1,000 RPMs smooth, not oscillating out. But again, that's assuming that you have the correct angles. So if you guys think about this, you ever take a universal, not a swivel, those are different, but a true universal joint? I got them. I've actually got universal sockets and a universal joint. So this is your universal joint. If you put this on an extension, I guess I should have thought about first, and you spin this on your impact, you ever notice these suckers get wild? Like if you have it like this, let's put one more on there. If you have it like this and your socket's over here and your impact gun is over here, there's nothing canceling this out. I mean, you can even just see it. It's like it kind of binds, but the hooks joint theory is gonna basically cause your impact to be the same speed, but your socket's gonna be speeding up, slowing down, speeding up, slowing down. It's like it's wild. I know some of you've experienced that. That is with the universal joint. Now, if you are going to use an impact, you should actually use a swivel. You'll also notice that it's black, so you know it's better for the impact anyway. So if you look at this, this doesn't have that universal joint design. This is more like a ball and socket. Okay, this isn't going to have the same effect. In a way, this is actually a lot more similar to a CV joint. You're basically looking at the difference between a universal joint and a CV joint right here. They do a similar job for you, but one of them is going to be a constant speed, CV, constant velocity. And one of them is going to be hold on tight. This is going to be fun. And if that socket flies off there and breaks the window or something, that's how you know you weren't paying attention. Okay, so now let's pause for just a moment. If you were to use technically one universal joint and an extension in another universal joint, and you were to have your impact gun at the exact same angle as the bolt, they would actually cancel each other out. It actually worked pretty good. But that doesn't change the fact that it's chrome. It's a little bit harder metal. We don't usually like to use those on impact. Impact like softer metal, thicker walls type of thing. Okay, so if you guys are understanding what I'm saying, 1,000 RPMs in, it's fine that it's going to vary the speed on this shaft because that's going to equalize out this output shaft. Get me? Now, jump to here real quick. Remember, this one was at 30 degrees. It was oscillating a lot. So how can we minimize that vibration? The flatter we get this drive shaft, the better. So I want you to keep that in mind because sometimes we got these, trucks, especially like a Jeep. I actually have a Jeep right over there. If it's not my Hummer, do not confuse the two. I would be offended. One is like there's only one, and then the other one had a different slogan like nothing else, so it was way different marketing campaigns. So on that Jeep, it's really short, and you got the transfer case here and you got the axle here, especially if it's lifted. You got to have that angle of that drive shaft super steep. Jeeps would be notorious when they're lifted to do a vibration because the more steep this is, the more accentuated the Hooke's joint theory is. All right, so we got some fixes for this, but I just want you to keep that in mind. The flatter this drive shaft is, the less you're going to experience this. But as long as you have your input and your output at the same angle, they should cancel each other out anyway. All right, so it's hard to get them exactly the same though. Now here's a little bit more of the exploded view of the parts. So here you've got your slip yoke that slides into the transmission. We've got our first U joint. This U joint on the side to side caps off of that cross are going to be installed in the yoke. All right, so a lot of times they'll call this the yoke. And then on the up and down cross and caps, that's going to be installed on the actual tube of the drive shaft. So your yoke is attached to your tube by the U joint. So if you needed to change a slip yoke, remember we had some discussion, oh, you need a new slip yoke. No problem. You can get a new slip yoke. But to change a slip yoke, you got to press the U joint out. And you don't press, it's like pressing a bearing. You don't press an old bearing out and then press the same new bearing back in. If you're changing a slip yoke, you're changing that, at least that U joint. And if you want to change universal joints, you can. I did a video. I could do a video too, but you guys watch the videos. One's a Chris Fix video. Chris Fix does amazing videos. It might not be the most technical, but you can see well, you can hear well. He spends a lot of time editing. He'll show you a way to do the U joint like in the driveway. If you were at the dealership and you wanted to change a slip yoke, you probably wouldn't do the U joint. You'd probably send the drive shaft out, and a drive shaft shop would do the universal joint, and they're going to do it in a press. They're going to do a little bit different. They're going to put a new yoke on, and then they're actually going to balance the drive shaft. So it's kind of a better service, but it's a lot more money. If you wanted to replace a slip yoke and you're like, I don't deal with U joints, just get a part price, you're getting a whole drive shaft price, and you're talking $1,000, sometimes more, right? So the way we service these is going to vary tremendously depending on where you're at. You guys, and I'll include myself. Us are probably in the most privileged place there is. Like, not only in the United States, but you're in Southern California. People tend to have tons of money. They're struggling in other ways, but you at the dealership can be like, you need a new slip yoke, or you need a new U joint, or you need a center support bearing, or whatever. Sell the drive shaft. You're in a very wealthy area in Southern California, in one of the most wealthy counties in the entire country, and you're at a Toyota dealer, and Toyota tends to more be like, buy the whole drive shaft or you're not our customer, right? So the repairs that we do are going to be very different than even where I grew up in little rural upstate New York. I did a ton of U joints. So if there was a problem with this yoke or this U joint, I'd press the U joint apart and I'd put a yoke on it and I'd press a new U joint in. You can buy a U joint for like $20, 20 US dollars. Cheap money. You could buy a yoke for probably like 50. If I have $70 in parts and I want to charge 2 hours in labor, that's still a lot cheaper than $1,000 drive shaft, and it's probably going to be cheaper than sending it out to the drive shaft shop. Plus, where I was at, we didn't have a local drive shaft shop. I can think of like 2 or 3 different drive shaft shops within an hour from here, right? So if they're competing against each other, they're going to keep their prices low. So where I was at, if we did have a drive shaft shop, it was further away, and they were raising their prices because there's no competition, right? Now, if you're in Botswana, people probably don't have the money to buy $1,000 drive shaft. You're replacing U joints because you can get it for $20, right? So we will talk about servicing the U joints, but from a visual standpoint, you got to be familiar with all these parts and very familiar with the fact that if you take this U joint apart, this yoke can now be installed 180 degrees backwards. Make sense? So if you take a drive shaft out of the car, we don't necessarily need to mark the yoke of the drive shaft to the tube of the drive shaft because you're not taking that apart. But if you are going to disassemble it, you definitely would need to match mark those. Right. And so then we'll continue. This one in the back is pretty much the same thing. They'll call it the spider or the cross. It's got the caps. You can see it's got the needle bearings. They're held in by snap rings most of the time, but I'll show you another way they can be held in. And then if you zoom in here, this one's got a Zerk fitting. So what do you think we can do with that? We can pump the grease in there, huh? So from the factory, most of these U joints are non-serviceable. It's kind of like ball joints and tie rod ends and stuff. They've taken the grease fittings away, but an aftermarket one may have it. If you're doing a good service on a vehicle and you see one of those, you don't need to pump a lot of grease, maybe just a little bit of grease, and that's going to lubricate these rollers and should extend the life of the U joint. Now, another reason I'm going to say we are privileged, be very inclusive today. The weather here is ridiculous. Like, you realistically don't get snow. You only get rain like 4 months out of the year. These U joints have the easiest life of anywhere. When you're in the snow, in the rain, in the cold, especially when they salt the roads, these U joints, remember, they sit pretty low. Remember, if you recall the picture, I think it was right there. This rear U joint catches all the snow and the salt and the junk. The U joints, when they get a lot of that goop and the salty, slushy, nasty stuff, a lot of times that will tend to get past this little seal and it'll corrode and dry these bearings out. So in the factory vehicle in the Northeast, those U joints aren't going to last that long. So it was nice if you could pump grease into there. And there's a tube. So if you pump the grease right here, it actually goes through a passageway and it pumps up this cap and it pumps up this cap and it pumps up this cap. And if you were to do that every oil change or every other, you could really make that U joint last. So this is a nicer design, but from the factory, they're not going to give it to you. You can't have that. All right, continuing about the U joint. If you look, it's a little bit hard to see, but if you look at the tube of this drive shaft, the ears are up. See, the ears are up. The ears are at 12 and 6. Then if you look down here, the ears are at 3 and 9. See, the ears are right in the middle. This one was unintentionally installed out of phase. Right? So they can be installed out of phase. Especially if it's a two-piece drive shaft, it's got 3 joints and a carrier bearing. This one could be out of phase, that one could be out of phase, that one could be out of phase. So what do we do to prevent that if we disassemble it? Well, we can match mark it. We'll match mark it here, we'll match mark it here, we'll match mark it here. Okay, why do we want to do that? Well, I can explain it, but I can also give you a really specific example. I knew some guys who worked for, in fact, actually, I don't remember what company, but it was some municipal company. You know what that means? That means like a city or a town or like a water department or power or something that provided services. But they had a fleet of trucks, and a lot of those will have their own fleet mechanics or technicians. So I recall they were in like a hiring session and they were talking about who they want to hire and why. And I remember a guy was kind of not rizzing him up. See, I'm getting real hip, but like razzing him. I don't know if razzing him is still related with you, but this dude was saying, hey, at the fleet shop, we're paying 30 something dollars an hour. And then one of the instructors, because it was like an instructor, meeting to understand who's hiring and what they're paying, he was from, I think, like science, engineering, and math. And he's sort of like, well, what you're paying is equivalent to like what my engineering students start out at. He said, okay. And then he said, but what are yours? It doesn't sound like you really have any minimum requirements for the job. Okay. So remember, academic people, okay, another quote, they not like us. They not like us. Academic people think that your degree is what will make you good at the job or your certificate. Now, I understand I'm in that world, so I think there's a little bit of value to that. For example, if you pass the ASE, that tells me you know something. It doesn't tell me if you're good at your job, though. See, that's kind of the point here. But this guy said, well, what's your degree requirement? That was actually the question. He said, we don't require a degree. And the engineering dude just about fell out of his chair. He's like, so you're telling me you're starting people off the same price as my engineering students, but you don't require a degree? And then the guy said, well, it's not that we don't require training, but we don't require the degree because the degree doesn't necessarily indicate what you know about, let's say in this case, drive shafts. Make sense? So it's better that you pass the ASE, which is a third party test, and you answer a bunch of questions about drive shafts. And that tells me you at least know something. And then the guy kind of said, well, then why not just hire straight out of high school when they've had no automotive specific training? And he kind of said, well, I'll tell you one of the reasons. We hired a guy and put him in the shop, and we've had U-joints. U-joints would go bad on those trucks and they would fix the U-joints. It's a fleet shop, so they're trying to save some money to the company. That's why they exist. And they had a guy and he would do the U-joints, and about 50% of the time when he did a U-joint, I'm going to back up to this page, 50% of the time they'd come back with a vibration. So 50% of the time they'd be good, and 50% of the time they'd have a vibration. They'd have to send it out to the drive shaft shop and they'd have to have it balanced. And if you're looking at this, you're already thinking those statistics should correlate with something this technician is doing wrong, right? So they sent the foreman down and said like, hey, let me see you do this U-joint. And he noticed what the guy did. He just yanked the drive shaft out, pressed the U-joint out, put the new U joint in, pressed it in, and it was 50% of the time it was in phase and 50% of the time it was out of phase. So about half the time the thing would have a drive shaft vibration. Makes sense. So he got down to the bottom of it of, hey, this guy just didn't know something basic. He could see the video on how to do the drive shaft, but it didn't necessarily explain. You got to match mark that sucker first. So that way, when you put it together, it's still in phase exactly how it was when you took it apart. So they coached him and they trained them. The whole moral of the story was this place is hiring and paying good money, but they want someone who's been through training. And they weren't even really calling for college specific. If you could do training at a trade school, if you could do training even by very carefully filtering out who you listen to on YouTube, you know, and if it's anybody with a car and a camera, they could be giving you bad info, right? But if you were to find somebody who has the right qualifications to learn from, and then you therefore go and pass the ASE, to this guy at the fleet shop, that's more valuable than degree because that's going to minimize the chances of that thing being out of phase 50% of the time. You should at least be familiar enough to know I may not have a lot of practice with the U joint replacement, but I know that I need to mark it. And so if you mark it, you can probably not have those comebacks 50% of the time. See, so the guy just needed some training. The engineering guy was like really he was kind of upset. He was sort of like, well, then I don't understand why not just hire him from high school? And the guy explained that, and then he sort of said like, well, why don't you just train him on the job? And then the guy said, for us to try to train, we can train them how we want them to change the U joint, but to understand the fundamental basics of Hooks joint theory, we don't have people to do that. That's my job. I used to be the guy who'd show you more just how to use the tool, but if I was showing you that in the shop, I wasn't going to roll a whiteboard out and show you this page. I don't have this page at the shop. My role now is to get you to understand the basics and the fundamentals. Okay. So this is why we're going so far into Hooks joint theory. It's kind of like Ohm's law. You're never going to do calculate Ohm's law for a customer. Customer never comes in the service drive and says, oh, I have 12 volts and 4 ohms. What's my amperage in the circuit? They don't. But you have to understand those relationships so that way you can understand if you have resistance in the circuit, that's going to lower your amperage, right? Or if you have low voltage, that's going to lower your amperage. Cool. So understanding the relationship. Now, to mostly summarize, remember, when this input is going to the U joint and the U joint's going downward, slowest, speeding up, fastest, slowing back down, right? So it's all about that angle. How that angle changes is going to change the speed. Now, if you were to look at the input as a red line, or actually, sorry, the yellow as a red line, and then you were to look at this blue one as an output, this is kind of interesting. Your input would be the same in blue. Your output would be the same in blue. That's crazy. But in the meantime, your front joint is speeding up, slowing down, speeding up, slowing down. Your rear joint is actually slowing down, speeding up, slowing down, speeding up. See, so if they're in phase and they're at the right angle, this cancels this one out. They cancel each other out. They cancel each other out. They cancel each other out. They should constantly be canceling each other out. It's pretty crazy, huh? So that's pretty much Hooks joint theory. If you saw the video, they have a really cool trainer. You can actually hear the speed because they hold a card up against a reluctor wheel and they change the angle and goof around with it, right? But remember, the key is this input of the drive shaft, which is the output of the transmission, needs to be at the same angle as this, which is the output of the drive shaft, but the input to the rear differential. So like this angle right here is actually the differential pinion. This shaft right here is the differential pinion, and this shaft right here is the transmission output shaft. So in a way, really what we're worried about is that transmission sitting on the cross member correctly? And is that rear axle sitting in the leaf springs or whatever correctly? They need to be level. Cool. The drive shaft can have an angle, it can't have like an extremely steep angle, but it can be 30 degrees as long as the blue are parallel, right? So if we were to draw a line right here, infinitely, a vector, if you will, and this vector, if you will, if those are going parallel, you chilling. You chilling. You probably never need to measure that in a typical repair industry. However, if a vehicle's been customized, you may need to measure that. And the ASE actually may test you a little bit on measuring those angles. So I'm going to show you how to measure those angles in photos. Cool. So as we continue, here's one of your basic types of joints. This is just a rubber flex disc. If you had, for example, a independent rear suspension vehicle, that differential doesn't move with the suspension. That differential is like solidly bolted to the frame. So the transmission and the differential, they don't move. They're the same. What moves with the suspension would be the CV axles coming out the side. So with a design like that, let's say, I think the Supra's like that. In fact, that IS 250, like if it's a rear wheel drive car, a lot of them have gone to this. Rear wheel drive cars don't have solid axles with a drive shaft that has to go up and down. Now, rear wheel drive cars, modern, have a basically solid drive shaft because it doesn't move, and then the CV axles going to the independent suspension rear wheels do all the movement. Cool. So if it's like that, we might just need a rubber flex disc. This is just to allow very small angle change, and it'll just flex just a little bit. We don't even need U joints on these. That could be just a very small change. All right. Or when we were talking about that Jeep, remember if that Jeep has to have a really steep drive shaft, that's going to accentuate the hooks joint. Well, the thing is, if you split, let me back up a couple pages. If you were to split that angle difference between three joints, right, it'll be speeding up, slowing down, speeding up, but the output will be the same as long as these angles are the same. We've got a hooks joint mechanism here, a hooks joint mechanism here, a hooks joint mechanism here. It's splitting it three ways. So if it was a 30-degree, you'd get a reduction. You basically split the 30 degrees essentially kind of like three ways. The more U joints you have splitting it, the less accentuated it's going to be. So keeping that in mind, we might not have room for all that on a Jeep because it's a tiny little stubby little drive shaft, but we could do what this right here is a double cardan joint. So the input is going to this yoke. The output is going to this yoke, which becomes the input for this yoke, right? So there's basically a three-piece drive shaft or a two-piece drive shaft with three joints in the length of a single piece. Cool. So if you see something like this, you're like, what the heck is that? That's just because it probably had a pretty steep drive shaft angle and they wanted to minimize the hooks joint theory, but they didn't have the room. Cool. So this is a nice design. We do the same thing. You could measure all the angles. And then a really nice design, probably better, is this. Do you notice that it doesn't have a U joint here? What do it have? Constant velocity joint. So this is like a half of a CV axle. In this joint right here, it's CV, constant velocity. What is that? That's coming at the end. Okay, but just remember, they can put a CV joint in a drive shaft. Subaru is notorious for that. Subaru loves put CV joint. They'll have a CV joint with a big corrugated boot, looks just like a CV axle in their drive shaft, and they'll do it front and rear. So it's kind of cool. All right, now when we're talking about all this baloney, right? You got the big theory now. You're like, oh, hooks joint theory. I totally got that. Why do you care? Because if we have an issue and we need to diagnose the drive shaft, you need to understand these concepts. What can go wrong? We could have a noise. We could have a bearing noise. We could have a squeak. We could have a squeal. Remember, I was saying that rear drive shaft down here? I mean, that rear U joint in the snowy, slushy, salty Northeast. If that thing is getting salty slush on it, and that's going to dry out the grease and lubrication, and then next thing you know, it's got think of what happens with a ball joint, right? In the original state, the ball joint's well lubricated. It's like a nice fresh shoulder, well lubricated, nice and quiet, no friction, beautiful thing. But But then what happens with the ball joint? The boot gets ripped, right? The boot gets ripped and the grease comes out. It's kind of like this. If that U-joint seal kind of leaks and the grease comes out, next thing you know, the water and the slush and the rust and the salt get in there. It goes dry. Do you guys remember what happens with a dry ball joint? It's not loose, it's dry. Squeaks, creaks, right? So you could have a U-joint that'll squeak. The first point of failure is notorious. Get in the vehicle, put it in drive. As you accelerate, especially because you put more force on the joint when you accelerate, it goes. You'd be like, oh, it's got a squeaking U-joint. Which one is it? A lot of times you could put it up on the lift, or if you wanted to guess, it's probably the rear joint because that gets all the slop on it, right? The first part of a failure is actually going to be probably squeaking. Really, the first part would be like, hey, you look at those seals and you notice they look kind of wet, right? But that's kind of normal. That's typical anyway. So you'd say, just run it. It'll be all right. It's almost like when you look at a ball joint or a bushing, hey, the rubber's starting to crack a little bit. Like, yeah, that's what it does. So if you're going to sell it because it's like starting to crack and dry rot, you're going to sell every U joint, every bushing, every ball joint boot. You're going to sell everything in every car all the time. And I just don't know if that doesn't sound ethical to me because they're all run around like that. Right. So technically the first point of failure would be you see a little bit of cracking in the seal and you maybe see a little sign of grease coming out, but I probably run it. And then the next point is enough grease has come out and enough corrosion and water has gone in and it's dry and it starts to squeak. That's your typical first point of failure. So if the customer comes in with a squeaking U-joint, no problem. I'll make sure which one it is. And they'll say, yeah, you can do this U-joint as a good service. A better service would be to do both U-joints. Best would be, if you really want, replace the whole drive shaft. Is that a better repair? I really don't know, but it'll be clean. It'll look nice. Right? So that'd be the first point of failure, will be a noise. Sometimes they have a center support bearing that can make a noise. The U-joint would be a squeak, generally, if it's dry. Center support bearing, if the bearing starts to get really bad, it can actually be a growl. It's a growl that will vary. It's an ASE concept, by the way. It's a growl that will vary with vehicle speed because the drive shaft spinning is directly tied to the vehicle speed. Okay. It wouldn't be tied to certain gears or, ranges. It's just vehicle speed growling. Boom. That'd be the center support bearing. Okay. The next phase would be just like a ball joint. It goes from dry and creaking to it's worn out and now it's loose. So if it's loose, you got a couple of issues. This one's for you, Andres. If it's loose, you got two things. It can be loose this way, right? So like you take it out of park and you put it in reverse and it goes bam. And it's like, whoa, this transmission bangs. Well, maybe yes. But if the transmission isn't banging and it's turning the drive shaft, but the drive shaft now has all this play in it, it'll speed up a little bit and then it'll hit, boom. Then you put it in drive, boom. Then you put it in reverse, boom, boom. It'll actually make noise because the drive shaft U-joint is loose. So U-joints can cause banging. That would be a noise. But if the U-joint's loose, remember it was really critical about those angles. We need to keep the angles nice and tight. If the U-joint's loose, now the thing is speeding up and slowing down at different times. You're no longer really keeping it canceled out, right? When this is speeding up, this one's slowing down. Yeah, this one's speeding up a little early because it's loose, and this one's slowing down a little late because it's loose. And now all of a sudden, that Hooke's joint theory is bringing out a vibration. So loose U-joints cause vibration, 100%. Seen it many times. So that should square you away, Andres. But I'd like to add to that. It's not like a tire vibration. You get up to speed, you get 55 and you start to get a little shimmy, little tire vibration type of thing. Maybe you want to put them on the balancer. Maybe you want to check road force variation, do a force match, etc. This is different. This is like when you're accelerating and you push the gas pedal, it shakes. And when you let off the gas pedal, it feels a lot different. It might not totally go away, but this is a vibration where you can change with your throttle input a lot because you're changing the torque on the U-joint and it might make it way out of phase or bring it a little closer to phase, right? This is something you can change with your throttle. That's a driveline vibration. It's just a bit different. If you got a driveline vibration, that's when you definitely want to get down there and check those U joints really well. It would do the same thing if it's out of phase, by the way. But if they're loose, it's especially apparent when you're changing your throttle. It brings them in or out, right? So that's what's saying. Imbalance, run out, U joint condition, like loose. If it's out of phase, or if you modify it and you have a really extreme working angle. One thing I saw way back in the day on GMs, they came out with like the 4-door long bed, big 2500 HD, a 4-door long bed. That's a 4-door quad cab, right? With an 8-foot bed. That thing was like a boat. It was a tank. It was so long, it's ridiculous. If you try to pull in a tight parking spot, like you could never one shot swing it in. You'd always have to pull past, back up to kind of get the rear wheels. It was just long. Well, it had a drive shaft that was like a mile long. It was super long. And the thing was, when you'd accelerate, it was so long and it was just barely within angle, it would actually kind of like torque the leaf spring and it would change the angle of that rear axle like this, right? It'd be like this. It would squat a little bit. That would actually knock them out of parallel. So we're supposed to have our pinion angle the same as our transmission. This one wouldn't change. This one would be the same, but this one under torque would actually kind of aim up, and now you got a disequal angle. And so what happens if we have those angles and they're not the same? What do you think? What you think? They're not the same. That's going to
Nice.
vibrate. Vibration, right? So if the angles are different, that's speeding up and slowing down, not a noise, but a vibration. So the customers would say, hey, when I accelerate my truck, I feel shaking, but then when I let off, it goes away. So we look, the drive shaft looks good. The drive shafts, whatever, all the mounts are good or whatever. They actually came out with a TSB and they said, you know what? This thing is just changing angle too much. The drive shaft is so long. They came out, I'm trying to remember, I think they had a 1-piece drive shaft and they went to a 2-piece, or maybe it was a 2-piece and they went to a 1-piece. I don't remember exactly what it was, but they updated it to address that flex that was making an unparalleled input to output hooks joint problem. I've also seen where people do all sorts of crazy suspension and then this rear pinion angle ends up wrong. They actually make little shims that will let you realign the rear axle where it sits on the leaf spring. It's pretty trippy. So if you were to do some of these measurements and be like, hey, these measurements are off, by the way, I'm going to show you pictures of how to do the measurements, and you wanted to fix it on your custom build that's going to SEMA or whatever, you can shim that rear axle to really fix your pinion angle and get the vibration to go away. Is that what we do? No. Is that what I do? Not really. I can tell you can download an app on your phone. It's from Tremec, Tremec, and it actually, your phone can measure angles. So you can actually use your phone and set it on these different things. So that one's pretty cool, but it's not really the best tool, but it's something. All right. Now, if you consider what I'm saying, what we talked about, these pictures I think will help you visualize it. If you were to look from the top, this one's not centered. So this one's kind of weird, but as long as this transmission output is parallel to this differential pinion input, actually that wouldn't vibrate. As long as they're parallel, this speed up, slow down, speed up, slow down, speed up to slow down. That's going to fix it. Okay, so that's looking down. They would normally be much more in line with this. They can be a little off center, but this is a little extreme. But saying from the bird's view, looking top down, they can be slightly off centered. But the more critical one is from the side. So here's your transmission. Look at line A, and then here's your drive shaft, angle, 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 and then here's your C. So this is your differential pinion line. Really what we need is A to be parallel to C. It's really hard to measure that though. So the way we actually measure it is we measure the angle between A and the drive shaft. Then we measure the difference between the front drive shaft and the rear drive shaft, but calculating the actual level line. So like this angle A right here needs to be the same as B, and B and B become the same, right? So A to B, then the other B needs to be equal but opposite to C. So it's like kind of weird geometry, right? So now we've got a few angle relationships to deal with on a two piece. And then when you add all these up, ultimately, all the angles, let's say this one is a positive 15. This one would be a negative 15, a positive 15, and a negative 15. When you do the math for all of them, they need to be pretty darn close to zero, at least within a half a degree maximum. So this is pulled directly from Toyota Technician Handbook. This is not my spec. Right from Toyota curriculum. Instructional designer talked with an engineer. You will not likely find this in the service manual. So I've been in some arguments with people. We talked about things like tire wear. Can you use different tires on your all-wheel drive? Well, service manual tends to be a little bit vague. If I'm not in the position, but there are some people in technical training who can go talk to the engineer who designed the system, and that engineer can give the actual number, but it will probably not be published. This is one of those. This is information directly from the engineer. So pretty cool information. At least this is Toyota spec, within a half degree max. All right, so when we look at these drive shafts, a couple things to consider. They could be steel, they could be aluminum. Why? Well, steel could be cheaper, but when you start to factor, you want lighter, you want better fuel economy, you want lower rotating mass. Actually, aluminum may make more sense. Even though it's more money, it may make more sense. It's going to have some benefits. But the way we work on them is a little bit different. So steel was a lot more forgiving. You could bang on these. So when we do U joints out in the farm, you'd be using a socket and hammering on the drive shaft. Seen it done a million times. On an aluminum one, yeah, no, don't do it like that. If it's aluminum, you can easily bend the drive shaft. That's when we get into, we're going to show you the proper procedures using a press and stuff. But that's not to say you don't know someone who's done it with a hammer, especially on a steel one. I know it's been done. I've done it, but it doesn't really make it right. Cool. And then you can tell, just FYI, this is a front drive shaft. This is going right past the transmission. This is an Allison transmission. I recognize it. Going to the front diff. This one's going to the rear, but the concept's still the same. Typically, they won't use an aluminum drive shaft in the front because this drive shaft doesn't normally spin, only if you're in four-wheel drive, if it's four-wheel drive. So the aluminum would typically go to the rear because that one's turning all the time and we're trying to save fuel economy and emissions. Or if you're really cool, you get a carbon fiber drive shaft. So when I did M4 training, they were like, oh, look at this carbon fiber drive shaft. I don't remember the price, but I remember thinking like, I'd be afraid to do U-joints on a carbon fiber drive shaft. If I even messed that carbon fiber drive shaft up, it might cost me my whole entire motorcycle just for one drive shaft. So that'd be a no for me. Part of the reason I would prefer aluminum. All right, so now the difference, this one right here, and this is shortened up. They're not this short, okay? It's ridiculous. This one would be on a two-wheel drive. See, the slip yoke actually slides right into the transmission. It rides on the output shaft of the transmission. So this can plunge in and pull out and plunge in and pull out. Remember, I told you guys a story of a kid who did a lift on his Tacoma. And after the lift, if he went over a big bump, the drive shaft would actually slip right out the back of the transmission. Well, that's why when your wheels go down, it pulls the drive shaft back, and that's okay. It's supposed to do that. But when you lifted it and now it's traveling down further than it used to, it doesn't have enough distance. The drive shaft's not long enough to make up that distance. It would just go right out the back. What do you think the fix is for that hypothetical situation? Gotta get a longer drive shaft. Gotta have a custom drive shaft made. They do that. They take your drive shaft, add to it in the tube. I don't really exactly know how they do it. A drive shaft shop, not someone in the farm with a hammer. Makes sense? The rancho. So a drive shaft shop could actually extend it and then also balance it and do all the details that they do. Cool. Now, if it's four-wheel drive, it's different. We use these companion flanges. So if you notice, the companion flange bolts right up to the back of the transfer case, and similar to the two-wheel drive, it bolts right up to the rear axle. So that's rigid. That thing doesn't have any slip. It doesn't slide in and out of the transmission. So what we need to do, we need to put the slip yoke in the drive shaft itself. Now, there was a question in our A2 review about worn thrust washers inside of a transmission. Well, now you know why. If this slip yoke was seized, it would be not able to compress. It would just ram all the gear train parts tight together, right? Whereas if it's lubed well, it's going to be better. If this one is lubed well, it's going to expand and contract. But if not, it's going to ram them together, right? That would be this is a perfect visual of that seized slip yoke causing premature wear in the slip rings in the thrust washers, thrust bearings, because it's putting too much force on them because it's not able to expand and contract. Cool. So part of the reason this is a combined unit is because there is some stuff that's combined. Even though the 9 out of 10 of it's going to be on A3, 1 out of 10 is going to be A2 material. All right. And then one more note I can tell you from experience. This slip yoke, how it slides, basically it has splines in here, and those splines spline with the output shaft of the transmission. We need that to have some sort of lubrication. Most of the time, there's plenty of ATF or, gear lube in there, but we did have problems on GMs where this slip yoke would actually kind of like slip stick. If you think about the slip stick situation, when would it be slipping and sticking? It wouldn't plunge well, right? The splines, it would just be stuck. So when would it really have an issue?
Bumps.
Bumps, it would do it. But when you hit a bump, you're kind of jarred in your seat. So customers would come in and they would complain. Basically, when I came to a stop, I was stopping, and then like as I stopped, right? Because when you're stopping, your back wheels are up. And then when you come down to a stop, it's got to compress. Well, it would pull it apart, but then when you go to stop, when it would try to compress it, it would stick. And then all of a sudden, when you really settled in, it would go boom, and it would move. And you could feel it. It'd be like bam. And you almost feel like this guy actually described it as when I stopped, I thought a bowling ball was rolling around in my bed, and I realized I think I forgot to take my bowling ball out, and it must have rolled out of its bag. And then he got out of the truck and he looked in the back, and it was like, there is no bowling ball. He's like, where's my bowling ball? There was no bowling ball. And then another different customer came in and said, yeah, when I stopped at the stoplight, I had to stop kind of hard. Normally I just coast, but I had to stop kind of hard because that yellow light kind of tricked me. I was going a little fast and the yellow came on. I realized I wasn't going to make it. So I stopped pretty hard. And then on settling, bam, I looked in my rear view. I thought I got rear-ended. There was no car. There was no car. Where's the car? Nothing hit them. What happened was this thing stuck, and then boom, it freed up. So there was actually a whole TSB. What the fix was, and it was on the two-wheel drive type. The fix was actually just unbolt the rear U-joint, slide this slip yoke out, and we'd lubricate it with a thing called special lubricant with PTFE. PTFE is like Teflon. So we'd actually lube the spline, slide it back in, pump it a few times, and then it would solve the issue. So just be aware, if you have splines right here, it's a good idea to, put some type of grease or something. If it's the internal slip yoke, this would be probably have a grease fitting right here. You guys ever seen the grease fittings on those? Because they have those. If you don't lube that, and most people don't, so I'm just saying, if you don't, that bowling ball situation is what can occur. If that thing can't slip, that's when you might feel like a slipstick, bam, like I got rear-ended. What's up? Okay, so you might get something like that, a diagnosis like that. So remember that. It's the whole reason I tell you the bowling ball story. Cool. And so you can see different types, similar. This is your center support bearing. That's the one that supports the middle transition from the front to the rear, two-piece drive shaft. That's the one that can have a bearing growl. They can also have the rubber fail. When the rubber fails, the angle changes. When the angle changes, the Hooke's joint theory becomes an issue. This can absolutely cause a vibration if it's loose, especially the rubber mounting material can be loose. If the bearing's bad, it's generally being a growl. Like the rollers are rough and they're rolling across each other. But that would do it on, basically lined up with vehicle speed. So the center bearing, vibration or a noise, depending on the nature of the failure. U-joints, squeaky noise or a vibration, depending on if it's just dry or if it's full on loose, right? So noises and vibrations are different, but they kind of go a little bit together. Cool. So this one's again similar to a rear drive shaft, except it's for the front, so it's a lot shorter. And the front is always going to have a slip yoke built into the drive shaft because the front of the transfer case, we don't have room for that drive shaft to plunge. And in the front diff, we don't have room for it to plunge. So we're always going to be companion flange if it's a front drive shaft, if it's a four-wheel drive. Or a type of solid bolted. It's not going to have a slip yoke. No slip yokes into the parts. The slip yoke will be built in the drive shaft. This is definitely when you'd see a grease fitting on a Tacoma. They still do have them on the front drive shafts a lot. All right, and then there's that center support bearing. And then this actually is more just getting you ready to understand. If you're going to take apart this U-joint, make sure you match mark it. Make sure you match mark it. And then this yoke is welded to the actual slip yoke that's going to go in, right? So be ready to do that work. Here's your slip yoke right there. You may call it the dangle arm. I totally made that up. If you call it the dangle arm, that's just weird. I'm the only one who called it the dangle arm, and it was only today. So whatever you say. But this is where the sliding occurs. See how this is all clean metal? That's good. If we got a problem there, which you'll see later, that's when it can tear the seal, right? So when we talk about the slip yoke, you got to be able to visualize this. This has to seal against that transmission output shaft. If it's pitted, if it's excessively rusty, if that bushing is loose, like we talked about, the bushing has to support this slip yoke, but it also has to be able to plunge. So quite a bit of things going on there. And then the splines should be lubricated to not have the bowling ball effect. This one is pitted. That transmission output shaft seal is not going to seal against that yoke. So what's the fix here? You guys tell me. How do we get this to be more like this? You could try to clean it. You could try to polish it. You could try to clean it up a bit with emery cloth. But the thing is, if it's pitted, the pits are, the pits are low. So if you go to sand it and polish it up and cookie disc it and all this stuff, it can clean the rust, yes. But if these pits are actual low points, you have no real way to fill those. You need to replace it. How to replace it? That's when you match mark it and you pull the U-joint off, you put the yoke on, you put the new U-joint in. That's how you fix it, or you sell a whole drive shaft. All right, there's a good example of that of that grease fitting where we have the telescoping type drive shaft. That's the slip yoke is built in the drive shaft. This is a front drive shaft. Cool. Now this has a different style. Do you notice this U-joint's exposed? On domestics, they don't have the companion flanges. They basically have the U-joint pressed into this yoke, but on this end, this cap of the U-joint goes directly into the pinion. The pinion has a little yoke on it. And then we put there's a strap and two bolts on those. So in the domestic world, we use a strap and two bolts right here. They don't give you the full flange, more like what we were showing before. Cool. So again, not a real big deal, but go ahead, shoot that grease fitting with chassis grease on oil changes. That's what you're supposed to do. Here's an example of that flange. Kind of a cool thing is you can see the outline. So when you go to put it on, don't flip it 180 because it's going to sit weird on the rust. put it right back where it is so it sits clean. But I will come in fact, I'll do it right now. But there's going to be a bit of review right here. Technically, the drive shaft is balanced as an assembly. So if you have a balanced drive shaft and you have a balanced rear axle, it doesn't really matter if you put this 180, right? In this case, it does because it's rusty and you don't want it sitting on that flaky rust and having it have run out basically, like a rotor. But if it's a pretty new vehicle and there's no rust, you can take the drive shaft out and you can put the drive shaft back in a different position and you realistically won't have a problem. But I'm going to prep you for something. If that ever had a vibration and they did what we call a field balance means you balance the drive shaft in the field. We balance the drive shaft in the field with it all as an assembly. So if this diff was a little bit out of balance, we can't add weights to that. We would actually potentially add weights in the form of hose clamps. You'll see, I got a picture, to the drive shaft. If we did that in the field on the lift using an electronic vibration analyzer or a dial indicator and we field balanced it to get the vibration to go away, it's kind of like doing an on-car rotor resurface with a hub that's messed up. If you take the rotor off and you put it in a different spot, now you've caused run out. If you take the drive shaft off and you put it in a new spot, you may potentially induce a vibration, but that would only be in the rear case that the drive shaft wasn't balanced as an assembly. It was balanced in the vehicle with all the drivetrain turning. Okay, so I want to make sure you're very clear on that because service manual a lot of times will tell you make a mark here and make a mark here and then pull them apart. And that's the safer bet. But it's the same with a rotor. If you follow service information, especially from ProCut or something, they tell you mark a stud and then mark a mark on the rotor, because if they were ever matched, cut on the vehicle, and you change that, you've now caused an issue, right? But realistically, that's not normal. So if you watch me and I yank a drive shaft out and I don't make a match marks, it's not because I don't remember. It's more like I'm kind of taking my chances right there because it's like a 1 in 1,000 that it was actually, done as on the vehicle field balanced, probably less, right? So it's not a real big thing to me. Similar with pulling a rotor off. But by the book, which is also by the ASE, you should match mark these. Okay. Now you know all the differences. Just don't run around your shop saying, "Hey, you didn't match mark that rotor. You didn't match mark that drive shaft from disassembly," because, well, some people may not know, but some people are going to know, and they're like, "Dude, just chill. Just settle down." Gonna make sense? Okay, but remember, if we're going to disassemble this U joint, you absolutely would need to match this yoke to this yoke if you're going to disassemble the U joint. I should be crystal clear right there. Everybody's good. If not, I'm going to move on, but you need to stop me and we're going to come back. Now, when we're doing an inspection, we're looking at this output shaft seal. We're looking for leaks right here. That's part of our inspection. And also, by the way, look at how rusty that yoke is. If that yoke were to plunge very far and this rust were to get sent into that rubber seal, do you think the seal will survive? No. So as long as the sealing surface is okay and we don't think it's going to plunge in really far, it could be all right. Like rust down here could be normal, but if the rust is closer to the seal and it looks like it's getting into the seal, that's when you need to change that yoke. If it's that slip yoke, if it's a vehicle that's commonly in use, the rust out here just means that's never actually going in and getting bathed with oil. That's the whole reason it rusted. But if it's a vehicle that sat, you could have rust all over the place. That will ruin your seal. You can put 3-4 seals in there. Sound familiar? Sound like our A2 review? Technician found a leaking output shaft seal, put a new leaking output shaft seal in, and then they found it leaking again, and then they did another one. What should they do? Do a third one? No, like look at the drive shaft slip yoke. Is it rusty? Where it's touching the rubber of the seal? Well, then that'll do it. Okay. Should get it. And then right here, we're grabbing the drive shaft. We're going up and down. That's mostly checking this extension housing bushing right there. It's a good concept for you. That bushing should guide the slip yoke and hold it where it's supposed to be pretty well. When we move it up and down, if it's excessive movement, we may actually need a bushing replacement. that slip yoke bushing, that output shaft bushing may be no good. Okay, so that could happen. That's what we're inspecting. And then here we're looking at a pinion seal leak. This stuff is rusty, but this is the rear axle right here. So this is leaking at the rear pinion. So this is all inspection. Additionally, if you look right here, we're trying to move right now. What we're trying to do is grab the pinion and grab the drive shaft and try to move the drive shaft. If the universal joints are loose, a lot of times you'll have movement right there, like up and down movement. Like here we are, grabbing it right here, hold it and move it up. That would be kind of like end play movement in the U joints. That does happen. Cool. We're here, we're looking at the grease seals. Remember I was saying the seals can start to leak grease, and this is where the water and the salt water and junk would get in there and really dry that out. That would be also a beach problem. So we got one of the dealers who works on the Huntington Beach lifeguard Tacomas, and they're having issues like this periodically. Right now, if you were to grab the yoke and the drive shaft and you're to turn them like this, that's checking for the U-joint looseness like this. So we got to check like this, but also like this. The U-joints can be loose in different ways. So right here, we're checking for U-joint looseness. If it's loose, it needs to be replaced. If it's loose, it's going to be inducing a vibration too. Okay, so that's how you would do that one. Not real tough thing. And then we're going to inspect the center support bearing. So we would grab the drive shaft, move it up and down right here, move it side to side. While we're doing that, look at the rubber, because sometimes that rubber can be damaged. It's actually pretty common. If the rubber's damaged, the drive shaft sags down and then it's going to get a vibration. Then on acceleration, it might move way up and it might get a different acceleration. If that rubber's bad, you're going to get like a driveline vibration, not like a tire balance vibration. It's going to be kind of dependent on your throttle. All right. And then right here, this drive shaft has a damper, and we're looking at this rubber to see if that rubber shot, if that damper's moving. Remember, I gave you a clue. There may be something related to like a dynamic damper. This is a dynamic damper. It's kind of like a harmonic balancer, but a lot of times it's on the actual drive shaft. If this damper's missing or this rubber's really damaged, you can even get where the rubber breaks loose and the damper will actually slide on the rubber. That would cause potentially a vibration. So that's all parts of the drive shaft inspection. Now, another type that kind of goes with the drive shaft, but it's slightly different, and it's not likely to be on the ASE, is called a torque tube. So we have an engine right here, and then we don't necessarily have a transmission on that on this system. We have the engine going to just basically like a little transfer box, and then that goes back to the actual transmission here. It's a very interesting setup. Actually, I got that backwards. The engine is in the front and it's got like just basically a bell housing, and this torque tube bolts up and it goes to the transmission, which is back here. So it's like a drive shaft, but all it does is connect the engine to the transmission. It's kind of weird. They call it a torque tube. That shaft is not exposed. The shaft is inside of a tube, inside of a tunnel. So they call it a torque tube, not really a drive shaft, but it's still kind of like a drive shaft, more just to get you familiar. If you have a front engine vehicle, but you have the transmission or transaxle in this case in the back, there may be a shaft connecting the two, such as the Corvette. And they did that up until they did C5, 6, 7, but the current model is a C8 Corvette. That's the mid-engine. They just moved the engine to the back. So it no longer needs a torque tube now. Cool. Now let's talk about noises. Like I was saying here, a squeak, that's probably like a dry U-joint. A clunk, that'd be a loose U-joint. Sometimes the loose U-joints can cause other stuff when you're going over bumps. They can do some interesting things. And then remember, if you have some of these issues, check for TSBs. So like, for example, I told you about that slip stick condition on a GM. That was actually and this is actually a slightly different one, but this is actually not greasing it. You're replacing the yoke with a new nickel coated slip yoke, right? So if you're in there doing all your own diagnosis and you're like, oh yeah, it's this slip yoke and greasing it, whatever, but there's a TSB on it with an updated part, you're not being a very good technician if you didn't know that. Okay, so checking TSBs, you can never underestimate how important that is. Extremely, extremely important. Cool. And now diagnosing, ooh, it's going to get a little bit tricky. I want to mention one tool that we commonly don't necessarily use. It's an NVH tester. We could do diagnosis of vibrations with the picoscope. You can get a picoscope with the NVH kit, and it will basically show you different vibrations at different frequencies. And you got to remember on a vehicle, things turn at different speeds. So you got the crankshaft turning at one speed. You got the pistons at a different frequency. You got the torque converter spinning at engine speed, but the turbine spinning at input shaft speed of the transmission. So those are at different frequencies. You understand what I'm saying? The engine's going 1,000 and the transmission input's only going 800. If we could use a tool to measure the frequency and we can kind of chart that frequency to determine like what order it is, like what the frequency is, what's turning at that speed, we can determine the source of it. All right. So um, you're if you get into this, you're likely no longer in Toyota land. So you're going to take some of this as like not super relevant to you other than just the theory, but you may end up in an independent shop. You may end up, at a driveline specialty shop. So I want to understand the theories right here. If you got those speeds, right? Crankshaft speed, which is the same as torque converter impeller speed, but torque converter turbine speed is the same as input shaft speed. Then you got planetary gear sets doing their different speeds, and your transmission output shaft speed is at a different speed, and the relationship between the two would depend on what gear you're on. But your transmission output shaft is the same as your drive shaft. Makes sense? So if the vibration correlates with drive shaft speed, then you kind of know where to look in the drive shaft. But then it goes into the differential, and the differential has a reduction 3.73 to 1, 4.11 to 1, something, right? So then those axles are turning at a different frequency, a different speed. And that's going to turn the same speed as the wheels, but the tires against the ground can have a little bit of a different frequency. So you can have all these different frequencies, and generally, in my experience, I don't really need the NVH tool because I have a bit more of a feel for it because I learned somewhat more through the School of Hard Knocks. If I drive the car and it gets a frequency that's very consistent at freeway speed, I'm like all over tires. And back in the day, we had a really hard time evaluating the tires, but now I'm gonna slam them right on that road force balancer, and I'm gonna know for sure if they're out of balance or if they have excessive road force variation, and I will know if the problem's the tires or not. And if it fails, I'm gonna say tires. And if they say I think it's a drive shaft, I'm gonna say no. Because I know what a tire vibration feels like, and I have a tool that verified the tires. And there's 1,000 tire vibrations for every one weird driveline vibration. Makes sense? It's just the nature of it. The tires are banging against your beautiful, well-maintained, even though the gas tax is the highest in the entire country, California roads. Makes sense. Bang, 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 bang. Those are getting beat up. Your drive shaft is not really getting that beat up. It doesn't hit the potholes. It might experience some weather in some areas, but your tires and your wheels take the brunt of the hits. Makes sense. And in other states and other areas and everywhere, it's just not that logical to think that the drive shaft is going to be the original cause of the NVH. But if I were to put the tires on that balancer and the tires were to be good, uh-oh, now I'm looking for something. But from experience, I can tell you when it's a driveline vibration, you can really modify the vibration with your pedal, with your throttle. Be like more vibration, less, more, less. Ooh, this is a driveline vibration. And from there, 9 out of 10 times, I can see what's up, right? So if it's got a weight that was knocked off during service, I can see that, hey, this drive shaft's missing a weight. There's a little broken spot weld right there. If I got a loose U-joint, I can see that. If I got a drive shaft that just had U-joints put in, I'm thinking like, uh-oh, this one's out of phase. Makes sense? I can figure out a lot of stuff based on experience and knowing the theories. However, back in the day, because I was GM guy first, we would have a lot of weird vibrations. And I specifically recall a truck that had a vibration, and my mentor and foreman were using this EVA. It was a noise vibration harshness tester called the EVA, electronic vibration analyzer. It was old. It looked like a Game Boy, not even Game Boy Color, like just basic Game Boy. It looked like TechStream Original, which is called the Diagnostic Tester, made by Vitronics, right? It was old school. And they were looking at some frequencies and some numbers, and they determined it was that drive shaft frequency. And then next thing you know, they're under there putting hose clamps on and goofing off, right? So, like, there is a place for this. It's just really abnormal. So if you overall understand an electronic vibration analyzer or a noise vibration harshness tester can analyze the vibration, telling you what order it's in, telling you what speed the component is turning, then you can determine, is it at engine speed? If it's at engine speed, maybe you're thinking a harmonic balancer. Is it at drive shaft speed? In which case, maybe you're looking at a drive shaft out of balance. Is it at axle speed? And maybe you're looking more at like tire balance. Make sense? There's different orders. That'll help you diagnose it. Cool. Now, further diagnosis tools. Here, this is to use to measure drive shaft angle, actual drive shaft angle, run out. If it's bent, you could also use this, believe it or not, for balancing. I'll explain it. And then an NVH tester from Pico, right? That's the NVH interface. The EVA tool, totally obsolete, completely obsolete. You could do the NVH tester. I may expand to do more on this, but it's not the highest priority. A lot of these basics we're covering are a much higher priority. So if I get these more dialed in, and I might add do a session on NVH, and you guys would be welcome to check that out. But let me see how my priorities are. Cool. Because like I just said, I was part of the old school. I saw them diagnose a car as an apprentice. And since then, I've needed to do it exactly 0 times. Cool. Now, when we're talking about doing these diagnoses, visual inspection is king, making sure you don't see, like what I was saying, the knocked off weight or the brand new U joints, etc. We can also measure the run out. I'll show you. Typically 40 thousandths would be the max. A bent or damaged drive shaft would need to be replaced. Cool. So here's how we're going to measure it. Clamp the vice grips there, thread this in, run the snake over to the drive shaft, set the dial indicator on the drive shaft at a nice perpendicular angle, not coming at a weird angle, coming nice and straight, and then spin it, zero it out, right? And then we're actually going to rotate the drive shaft, and then you're going to see how much it moves. Literally like checking run out of a rotor or anything else, whatever you want. And then hopefully there's a spec, but if you'll recall, we talked about a general rule of thumb, no more than 40 thousandths. So it doesn't have to be perfect. It's not like a rotor. A rotor, you can't really have more than 2 thousandths, but it should generally not be over 40. And you might find that in service info. If you find it out in service info, great. I love black and white. I don't like gray. I mean, for a car color, I think gray is one of the best. I like black too. I don't like white. I'm sorry. For a house, white, car, either black or gray. But in situations, I don't like gray. So if let's just say you're going to do this diagnosis, I don't want to say like, oh, look at it and see like, yeah, that's got some movement. Like, no. Measure it with the dial indicator and compare it to the spec. The spec tells you if it's good or bad. It's not like, what do you think? What's your opinion? How many opinions you want? Everybody's got an opinion, and they're like butts. A lot of them stink. Probably all of them do. Is that weird? So compare it to spec if you can. But again, are you going to do this commonly? Probably not. If you see a damaged drive shaft, you're probably going to see a damaged drive shaft. If it's got a dent in it, and they're not complaining, I don't know that I'd make a real big deal. You might note it. But if they bring it in for a vibration and you can see where they clearly were off-roading and they high-sided and it was sitting on the drive shaft and the drive shaft is dented, like that needs a drive shaft, right? But if it's something weird and you want to measure the run out, just compare it to the spec. I like that. If you can visually see damage though, it's done. Kind of makes sense. So we'll rotate it, do the measurement. You can do it on both ends, do it in multiple locations. All that's going to help. Now, when we talked about phasing, disassembling, all that type of stuff. This is going to give you some of the procedures. But first, let's start with what we call driveline angularity. So this is the driveline angle measurement. We're going to need two things. One, this is a magnetic square, but it measures angle. We can also use a big protractor, and these together can do the diagnosis. When are we going to do this? Probably never, to be honest with you. Unless you're doing some major suspension modification, you don't need to measure this. But if a vehicle came in and they did like some crazy SEMA build and they're like, hey, this thing vibrates, first off, it'd be like, well, you did all the fabrication work. Setting up the drive shaft should be part of that. But if they're like, we don't know how to do it, we need you to master tech. I'm like, all right, cool. Then you need these tools. I don't even own these tools. We have them at the school. I'd like to do a follow-up video of measuring all these angles, but it would be its own thing. Okay. Because it's just understanding them is going to be adequate. For you to get practice and expertise is totally unnecessary because you're just not realistically going to do this unless you become a driveline specialist. All right. So keep these two tools in mind. As we go into this, we'll explain it. You want to check angularity. First thing, the vehicle needs to be level at a normal ride height. So good luck fitting under there. Where you think that you should do this if you want to be able to walk around at standing adult non-hobbit height. There's one lift in the shop that you can think of. Am I right? You can't have the wheels hanging. It's got to be at normal ride height. It's got to be level. You're going on the alignment rack, right? Do this job on the alignment racks. Perfect. Now you're going to put an angle gauge on the actual drive shaft. This one's nice because it's smaller. You can literally download that app. That would work. You need to know that angle. But the other thing you need to know the pinion angle. So sometimes if you're lucky, you can put the angle measuring tool on the pinion itself. So the pinion, remember the pinion's that rear diff. That's why we showed that picture. If you know the drive shaft angle and the pinion angle, you can see the difference. So if it's 8.1 degrees and 10 degrees, 10.5, that's 2.4 degrees. That operating angle, that's pretty flat, actually. That's a really nice flat drive shaft. So that's got a 2.4 degree angle. That means when you go up to the front, you need to have the equal but opposite angle. Make sense? So that's how we're doing the math. That's how we're doing that measurement. Okay, it can be a little more tricky. So see, if you look at this one, this was on the differential pinion yoke. So this is measuring the pinion itself, pinion angle, the actual drive shaft. Then on this one, it's hard to measure the transmission output shaft angle because it's inside, difficult to get to. So where we have this, and it's a little hard to see, I acknowledge, and this is part of the reason the phone doesn't work real well. You actually have it on the U-joint cap, right? So you see this U-joint cap? You wouldn't be able to use this U-joint cap because this U-joint is pressed into the shaft itself. We don't care about that. We need to put it on the U-joint cap that's pressed into the yoke that goes into the transmission. It really comes out of the transmission, actually. So you understand we've got it on the yoke U-joint from the transmission. Cool. That's a really tough picture to see. I get that. We're going to show it one more way, right? And then if you've got a 10.5 at the yoke of the output shaft and a 1 degree at the drive shaft, you got a 9.5. Those would actually be not equal, by the way. So that could be a problem. Here's what I was trying to say. You've got the output shaft coming out. You see how you'd have a little U-joint cap right there? You'd put your angle measurement tool on that, but then you'd rotate it up to the top at 12 o'clock and you could actually measure it there. Here's another look at that. If you're looking at this one, here's your transmission or your transfer case axle shaft. You'd put the tool on this U-joint cap. Okay, that's the one. If you really wanted to, you could measure the flange using a plumb bob, and you could measure the drive shaft, using this one here. But that's one way too, but this one's a little more Toyota engineer, like we'll spend all day on it. We're going to get a plumb bob and a string and hang it. And of course, gravity is going to pull it perfectly perpendicular. And then you can actually measure that angle. But the more practical way, this shaft right here is going to literally control where this cap sits. So if you can just measure right off that U-joint cap, cool. But it takes a special tool. So you actually have to have a tool that'll sit on the U-joint cap, and then you can put your gauge on the tool. So that's kind of the pain in the butt thing. Whereas this one, you could make yourself a plumb bob using a shoestring, a shoelace, and a rock. And then you just have to have a protractor. So technically, this is the way you do it if you were in like the third world. But if you're in the first world and your bigger concern today is about what you're going to have for lunch, then you're probably just going to say, you know what, let me just go buy the tool so I don't have to do all these longer steps. Okay. And so this one's using the plumb bob, and that's how they're coming up with the different angles using a protractor, right? It's not really that complex, but I mainly just overall want you to understand it enough to be able to answer some basic questions and have a conversation and understand why when a customer starts lifting and lowering the vehicle, they're playing with stuff they don't understand. I will guarantee you they do not understand this. Very few do. Cool. So there's all these measurements, and you need to be within, there'll be an allowance. It's tough to say exactly what the allowance is, but you need to be within a half a degree according to Toyota engineer, remember? So that was a bonus. So not this degree, but the difference between this front angle and this rear angle, those need to be within a half a degree, closest to zero as possible. Cool. So with that being said, that's how you determine the angular operating angles of the U-joints. They may call it drive shaft angularity. And then again, as a reminder, if you're going to pull that drive shaft off, a match mark is the best practice. But like I was saying, if the drive shaft was balanced independently and the differentials in balance, wherever you put them on, it shouldn't induce a vibration, right? Unbolting these companion flange, prying it out, just be careful with that. If it's going into the open yoke, not the companion flange, it's a good idea to run electrical tape around these caps. Do you know what happens if that cap falls off? Remember those little needle bearings? Those things fall in, they fall out, they fall down the drain. Like you can mess one of these up. The good news for you, Toyota people, the companion flange, you don't really have to worry about that. The companion flange is so nice, but the domestics save a little money not doing the companion flange, and they have the U-joint seat right into the pinion yoke, and the caps are held in by nothing once you undo the straps. So tape them. Cool. You can see this is a good image of the strap, right? The strap holds the cap directly. You take these bolts off, you take that strap, and then this cap can fall out. So be careful. And then look at that. What do we got right there? That's another spot you may see a Zerk or a grease fitting. So if we wanted to grease that, you'd have to get the grease gun on there. Sometimes you can, and sometimes you need a special one with a longer needle to pump that grease fitting up. The ones on the end of the cap are a little bit nicer, but then they can also get hit by something. So they do make one that's a very low profile grease fitting, but you need a little needle grease gun to pump those. Cool. So you got some options. See a little bit of grease coming out, that's good. This boot's a little swollen, that's good. That one's perfectly great. You don't blast the thing so grease blobs all over the place. It's just excessive. All right, more parts of service. We need to balance this drive shaft. When I say we, I don't mean us. I mean someone else. So look, it's not commonly done. Many shops are not going to buy all this specialty equipment. There might be one shop in your area that does drive shaft balancing, and they balance everybody's drive shaft and they get all the business. Cool, that makes sense. That way we can keep the cost down. The beauty of the free market, right? But there are methods of field balancing a drive shaft using hose clamps. But generally we don't really do that. That's like, I'm telling you, it's interesting. I feel like I'm always in two different worlds. I came up right at the end of old school when we were doing crazy stuff. And then the recession changed a lot of stuff, and business got leaner and meaner and Just the way we did stuff is different. And we're no longer super concerned about saving the customer that much money. We're just like, you know what? This one's getting sent out to the drive shaft shop. Back in the day, we were doing some field balancing, but it was just as I was an apprentice. I never even did it as a line tech. Cool. So if you want to balance a drive shaft, here's what you have to do. You have to have this special machine. You have to put it into this yoke. You have to bolt it down right here, set the angle, turn this thing on, set the test speed. You want to measure it at 1200 RPMs. No problem. You're going to measure. It's going to give you numbers. You're going to look into it. You're going to be like, hey, it needs a weight right here. You're going to make a mark with that weight. You're going to hold it there temporarily. You're going to tape it up and spin it again. And if it fixes it, cool. And if you like it, then here's your final. You had the rough draft, and here's your final draft welded in place. Do you think that this is what we're going to be doing? Are we going to do this? This is what a drive shaft shop does. That's what I'm saying. Balancing it is actually not that different than wheel weights, except you have to weld them on and you need the special machine. It's not really rocket science. It's just, look at this thing. We're not going to buy this and keep it in the back of the dealership to balance 2 drive shafts a year. It don't make no sense. Cool. But look at that weight right there. That weight was on, taped to make sure it fixed it, and then welded. What happens if that weld were to break and that drive shaft weight were to fall off? What just happened to the balance? I think you know. It no longer balanced, is it? So if you see weights, do not remove. Do not. If you see a spot weld that looks like it was broken, a weight probably flew off. In which case, you probably diagnosed the vibration, haven't you? See, that's why I don't really go all crazy on the NVH kit, because it's usually something you can kind of tell. Cool. Now, field balancing. This is literally 2 hose clamps. And what we would do, I'm going to describe this, and you don't need to memorize it, but you need to kind of understand it. If on the ASE you see clamps like this has been field balanced. We don't weld them on in the shop. We put a hose clamp on there. Where's the heavy part on the hose clamp? Where the screw is. So this becomes the heavy part. What we would do is if it had a vibration, we thought it was a drive shaft, we'd put a dial indicator here, and you would actually, it's a little sketchy. The other thing, okay, let's make it less about a dial indicator. Let's say, you see how this has a China mark, a China pencil? You'd basically rig up something where it's holding the pencil near the drive shaft, and you'd spin the drive shaft, which I'm going to do with, let me look at something that could be round. Let me use this paint can right here. Okay, you can see this. We'd use this China pencil. I'm actually going to use a real Sharpie. Okay, you'd put this marker like this, and you'd spin this drive shaft. Let me get it on a white background. Yeah. Oh, my stupid hands in the way. And you'd spin this thing, right? And if you got it up to speed and it had a vibration, think about it. Like if right here you had a heavy spot where I marked it, when the heavy spot would come down, the drive shaft would dip a little bit and the marker would hit it. And then it'd be spinning, 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 and the heavy spot would come down and it would hit it. And then the light spot would be down and the heavy spot would be up, and it'd go up, and then the heavy spot would come down. And every time the heavy spot comes down, it would hit your marker. So you'd literally rig something up and spin it. And when it would vibrate, it would actually come down and it would leave a mark. And by the time you see a bunch of these, that's how you know there's a heavy spot right there. If there's a heavy spot right there, you'd go to the opposite side of it, make a little white mark like this on screen, and then you'd put the hose clamp there. Boom, you put it there, and then you'd respin it again. And if it was still vibrating, you do the marker thing again. And now the marker thing is touching in a slightly different spot on the other side. So you make another mark and you put the hose clamp there. All right. So that's also not really rocket science. We're just not balancing it electronically. Literally, the heavy spot will pull the drive shaft down and hit your marker, hit your China pencil in this case. Okay. And then you put the weight exactly opposite of the heavy spot to balance it out. Cool. You guys kind of get that a little bit? Okay. It's a little scary though, because you got to have the vehicle turning. The drive shaft's got to be turning at like 1200 RPMs. You get, all right, see what mark is down there. It could be kind of gnarly. You know, they used to balance tires on the car with the car moving at 55 miles an hour in the bay. They don't make them like that anymore. You know what I'm saying? That's when the men were men and the women were too. All right, but then let's say we go to reinstall the drive shaft. Why do you think we'd want to lubricate this slip yoke on the outside? Why would that be helpful? We definitely want to lubricate the splines. I think we got that. But what about the outside?
Friction.
So when we slide it in, that metal is going to go up against the output shaft seal. And if it's dry metal on a dry seal, you think it's going to probably kind of wear the seal out, right? So if we lube it up a little bit, that's just going to help to to prolong the life of that lip on the seal. Cool. So that's what we're doing here. Right. And then we're going to go ahead and probably have those internal splines lubed, and maybe that internal spline being lubed is going to lubricate the output shaft spline, but then we're going to go ahead and slide it in. And if we made a match mark, which is the preferred practice, make sure we line that up when we go to the rear diff. And we're going to bolt it up and torque those, because if a drive shaft comes loose, okay, sometimes I'll make myself really humble. When I was an apprentice, I left drive shaft bolts loose. Like later that day, my mentor got a call because he was actually friends with this customer more directly than just through the dealer. He's like, "Hey, I got a horrible vibration." And he thought about it. He's like, "What did we do?" "Oh, yeah, we had the drive shaft out." "Okay, I think I know what it is." And he showed up at the guy's house and tightened those drive shaft bolts. So the drive shaft didn't fall out, but he told me I got my butt chewed out. Rightfully so. If you leave a drive shaft bolt loose, they don't just fall out and the drive shaft just hangs out. That drive shaft will come off the rear diff and swing, and it can actually hit the ground. It's even flipped vehicles over. That drive shaft has hit fuel tanks and broken fuel tanks and potentially started a fire and burned an entire family alive inside the vehicle. Okay, we can go extreme on this. You really need to make sure those drive shaft bolts are tight. That you need to make sure every bolt is tight, but this is actually just as dangerous as like a brake caliper or a wheel. Right? If you bolt an airbox in and you leave a bolt loose and the airbox gets a little loose, like, I'm not saying that's okay, but like if a tail light's loose and the tail light kind of rattles, makes sense. This is something you got to be really careful with. All right. And then for support bearings, we're looking at the mounting. This one's pretty rusty. That's getting a little sketchy. That's scaly rusty. We're looking at the rubber right here. If the metal support is failing, that's going to cause a vibration. If the rubber's failing, the drive shaft's going to move and it's going to mess up the angles, and that's going to cause a vibration. If we're turning this bearing right here and we feel a roughness, what do you think that would cause? Give you a clue. It wouldn't generally be a vibration. It would be
It would make a noise.
exactly like a growling noise, and the noise will be consistent with vehicle speed. All right. So if it's a rubber and it's loose, probably a vibration because the hook's joint angles. And if it's a bearing like the rollers, probably a noise because the roughness of the rollers rolling across the race, right? Both of them would require a center support bearing. So I want to make sure you understand both failures, because somebody would say, "Oh, a center support bearing causes a vibration." Say, "Well, it can." And then someone else could say, "Oh, no, it doesn't. It causes a noise." Well, it can. It could be either one, depending on the nature of the failure. Cool. So here we're going to change a center support bearing. So we're going to just cruise through some of the steps. And again, are you going to change a center support bearing? Probably not. We've changed some at the school. There's even been some shops that have changed them. But generally, what would you do if it needs a center support bearing? You speak for yourself. What would you do? Dealership. Probably going to replace the drive shaft. If you're trying to save the customer some money, what would you do? Dealership probably going to send it to a driveline shop, and the driveline shops can do this. However, if it's your car and you really want to save some money, what would you do? You could replace this. This is a doable job. We used to do these all the time in the shop. We don't do it so much now, but we did. This was fairly common back in the day. So we'll go through the steps. Make marks. What'd you say? Repeat,
Replace the
Roberto.
bearings.
Yeah, exactly. That's what I would do. If you could buy the center support bearing cheap. If you can do the labor yourself cheap, you can fix this for cheap. So relevant for you guys on your own, but relevant for people who are, the dealership is not in business to save the customer money. They're in business to provide a very high quality repair. So we're not thinking like, oh, let me find a way to be the cheapest. The dealership's never going to be the cheapest. But if someone's at an independent shop, they're going to say, well, let me find a way to provide a cheaper alternative and take really good care of the customer, because they need to take good care of their customers or they don't have customers. The dealer, you know where they get their customers? Generally from sales. They sell a car and the customer is automatically a customer for the dealer. So the independents, they have to treat their customers a little different. Maybe I might even say, to have a good business, they probably have to treat them a little better, right? So if you want to save money, here's what you can do. Make a mark, because you see this bearing, it won't come off unless you take this yoke off. You can't take this yoke off unless you press this U-joint out. If you press that U-joint out, you need a new U-joint. Okay, so this is not a minor little tiny job. This is going to be more of a bigger job, but it's doable. So you take the U-joint off, press it apart, take the nut off, slide the yoke off, and then you're going to use some sort of remove any snap rings that are in there, and then you're going to have to come up with a way to pull that bearing. So this is a gear splitter, and this gear splitter is on a press, and we've got it behind the bearing, and then the press is actually going to press the drive shaft out of the bearing. Okay, so we have all this stuff. A good shop would have all this. A little note though, this was good. They have the plate bridging the gap between the blocks. That's good. You never want to have this 90 and have the bolt going across the two, because then you're putting all the stress on the bolt, right? So this is we're doing a great job here. All right, and then we're going to inspect the spline, check it all out, and then we'd actually press the new bearing on, get it into place, add the snap ring, circlip, whatever it was, a lot of times it'll come with like a new bracket, line this yoke up. Do you notice we're lining the yoke up to the old line we made? If you didn't make the old line, you really messed up. Like I'm not exactly sure what the heck you're going to do. You might be able to figure it out. Or you might just be wrong. If you were to have that not lined up, what would the symptom be? You guys remember? They're no longer in phase. What did that cause? Vibration. So you may be like, oh yeah, we'll bring your car in and we'll fix your noise that's growling with vehicle speed. Then you give it back to them like, well, now it has a vibration. Yeah, because you didn't match mark it and you have it at a phase. Makes sense? So that's why it's valuable for you to understand the theories of these processes, even if you don't do center support bearings, but you go and you work for this municipal thing and they hire you because from experience, someone who's been through a class and has passed their ASE is not going to be totally oblivious to the fact that you're supposed to mark this stuff. That's the logic right there. If you pass your ASE and you got a patch right here, good. That doesn't mean you can fix the car. It just means you won't be totally clueless to the fact that you're supposed to match market. You understand? Somebody in the business for real is going to know it is valuable, but it doesn't mean you're not a paper tech. You could pass all these tests and not actually be able to do any of the work. You'd be a paper tech, but it still does have value. Cool. Going to place them back together, line all these up, press the new U-joint in. The new U-joint's held by those clips. We're actually going to talk about how to change a U-joint in just a second. Get it all back installed, and there you go. That's how you do the bearing. You want to do U-joints? Different types. U-joints can have this type of end snap ring. They can have this type of inner snap ring. They can even have this thing, which is crazy. See this little white dot? That's what's called a plastic injected molded. So the snap ring holds it, the inner snap ring holds it, or no snap ring holds it. They literally set it in place and there's a groove in there, and they inject hot plastic and the hot plastic holds it. It's pretty nuts. When we go to work on it, here are the tools. So this is a U-joint press typically. The Tiger tool is a nicer tool. That's like a brand name. So either way, we're mostly going to focus on this type because this is a little more typical. It looks like a ball joint press. Some of the ball joint presses can also do U joints. All right. And there's a couple other ways to do it, some of which are better than others. All right. But here we go. Remember, we got to match mark it. Again, match marking, match marking, match marking. So when we reassemble it, we know it's right. Take that snap ring off. You guys can see literally just needle nose. You might have to remove grease fittings if it has them, because otherwise you'll break them. Mount this press in the vise. Using this press, you're going to see we're going to actually line it up where on the one side of the press, you've got the it's kind of like the female right here. See this female? That would accept a U-joint cap. This side's the arbor. That's going to actually press directly on the cap. See, this cap has been driven in. If you drive this cap in, it pushes the cross or the spider, which pushes this other cap. You're going to actually push that cap like just about out of there, and it's going to fall inside the one end of the press. So if you remember the press, see there's this side and there's this side. This press right here, this has to support the drive shaft really well, but accept the cap to go inside of it. Boom. Cool. And then as we press that in, then eventually the cap will pop off. See, this cap's actually ready to come out. If you do it just right, you might be able to get both caps out, but sometimes you'll press it in enough where you could maybe slide the one cap out and then press it the other way to slide the other cap out. There's a little bit of a dance there. But ultimately, this cap is out now. See the grease? There's needle bearings in there. This is generally why we are not going to really reuse this. It's rusty to try to drive it all back through there, and the needle bearings and the grease, like it, you're not going to reuse a $20 U-joint. Even if you're really careful, it just doesn't make a lot of sense. All right. And then we'll have to press it the other way. Right. So we got to press it one way, remove the cup, generally press it the other way, remove the other cap. And then once the caps are out, that's when this cross can be free and you can actually get the yoke off one side. Now, do you see if this yoke is off, you could actually accidentally put it 180 out? That'd be a big problem. So you've got half of the U-joint apart now. If you're doing the yoke, the yoke is off, but I still wouldn't put a new yoke on there and reuse those U-joint caps. I'd continue the process, pressing the caps off of the drive shaft side, right? So you see they're in the drive shaft side. Right now we pressed them off the drive shaft side. Now you can pull the cross out all the way. And then you can clean this all up, make sure these grooves are good, because you have snap ring that needs to sit in that groove. And they can vary. Sometimes the groove is in there, and sometimes the groove is on the U-joint and it's on the inside, like those other ones. So let me back up and remind you, we have these types. This is where we're cleaning the groove right now. But in other ones, we have these types. The groove is actually in the cap. Cool. These ones are one-time use. So I'm going to show you how to take those apart. And then at the end, we're going to put a snap ring in instead. Right? So we pressed the cross, we pulled the cross, we cleaned the groove. We installed a new one with no grease fitting, no Zerk. There's going to be a special adapter to make sure we press this thing and we don't damage the cap or damage the joint putting it in. Here we can start it. You can see you can push this cap down and get it started, but you actually have to press it all the way in. When you're pressing this one in, the female side would be over here. The male side would be over here. Cool. And you got to have both caps in when you start this. So we're going to slowly start to run it, right? This one is the adapter. The male side is pushing right on that U-joint cap. You could, this is where on the rancho, you'd be using the hammer. Use a socket that's the size of that adapter and you'd be banging the hammer. The negative of the hammer is this. Well, there's a couple negatives, but the main negative is it shakes those roller bearings, those little needle bearings. It shakes those around. If a needle bearing falls in, this cap will hit the needle bearing. It won't seat all the way. And you'll just be like, what the heck? It won't go in. I can't. And you just keep banging on it and you'll crush the needle bearing and you'll have ruined your brand new U-joint. Don't ask me how I know. Okay. I just want you to know that I know. And I don't want to tell you how I know more than one time. All right. But if you get it pressed in all the way, going to put the circlip, put the snap ring on one side, Then you flip it to the other side and you're going to install the other cap. And if this U-joint clip is in, if the snap ring is in, you should be able to push up against the snap ring a little bit from the other side and just barely fit the snap ring on this side. Make sense? If you overpress it, you'll actually damage the snap ring. If you underpress it, you won't be able to fit the snap ring on the other side and you have to press a little bit more. When you're done, move it. If it moves smooth, good job. If it doesn't move smooth, you might look and you might see one of the snap rings is kind of like bowed like this, and you'll be like, oh, push that one back down because you're kind of trying to center it. And then it should move freely. Put the grease fitting in. Again, if you were going to do this, there's different methods. So this would be one that had the snap rings. Ready? But this is one that doesn't have the snap rings. This one, you see that little dot? That's the plastic. It leaves like a little tail. So you'd rig it up in the same press and you'd start to press it, but it wouldn't really work yet. And then you'd get the torch out and you'd make this piece a puddle. And it can't be tight if it's a puddle. No, I'm just kidding. You're just going to heat it up a little bit. And as you're heating it up with the torch, this stuff will start to like ooze out of it. And you're going to heat it up and all this junk is going to ooze out. And then all of a sudden it'll be freed up and you'll be able to press it. So you're heating it up to make the plastic liquefy, and it's basically going to back itself out, relieve the pressure. And then all of a sudden you hear a pop and the U-joint will be freed. Cool. So that's the plastic injected molded ones. If you see a torch on there, they're melting the plastic out. Okay. Then you press them out. You can see this one's still smoking. I like that one. I can smell that. I can literally smell that picture. I know exactly what that smells like, and therefore just seeing it takes me to the place. I know how it smells. Cool. It's like if you see a picture of leaves in Vermont and you can smell the pumpkin spice, kind of the same. Then when we press the new U-joint in, look, you see this? We will put a snap ring on the internal of these and we'll just abandon all that plastic molded. We don't have to re-plastic mold that. We don't do that. We use the snap ring style. Cool. So you bust the plastic molded to change it, and then you put a snap ring style in. Cool. Now we're on to something totally different. Drive shafts, you should be decent on. Do I expect you to do a lot of the work? Not so much. Do I expect you to understand the concepts? I'm telling you, you need to understand the concepts. They'll be on ASE, plus you'll be actually diagnosing some U-joint issues. That does happen. You may not do a lot of the services, though. I'll give you that. New thing, front wheel drive vehicle. So we're no longer talking about drive shafts. Drive shafts in the hook joint theory, there are some negatives there. If you were to try to put a regular traditional drive shaft with U-joints in the front of the vehicle, it's not going to work well. And the reason why is because of this. You got the transaxle, and then as you're going over bumps, this angle is going to change. And if you look at it, the hub angle can't be the same as the transaxle output angle. So if this angle is constantly changing, and even imagine this, you're steering, right? When you steer, that angle is drastically different than the transmission output angle. You have no way to do equal but opposite canceling out the hooks joint theory. You understand? You can't do a U-joint on the front axle. So if we're to go back in the day, and this is where that fun video was, that one is a classic right there. But if you were to go back in the day, the cars were rear-wheel drive. So we didn't run axles to the front wheels. They had a lot of stuff to figure out when they wanted to go front-wheel drive. One of the main things was actually the axle. How are we going to turn the wheel from a transaxle and have it not have a vibration? Can't use U-joints. Universal joints aren't going to work. So they came up with this thing called the constant velocity joint. Do you understand why it needs it? These angles are all over the place. Cool. So here is an example of a tulip, or sometimes called the tripod. I've even heard it called the tripod with a T. That was in the video. Joint. We got a clamp, a boot, and an inner clamp. We've got the tripod. These parts, I believe, are called trunnions, and then a snap ring, and that's all assembled into this housing. So this is going to come out of the transaxle, and then out of this spline, we're going to get the actual CV axle that'll go to one more drive shaft. and then, or to one more joint, and then ultimately to the hub, right? And then you'll notice this ring right here, this little snap ring that goes inside the diff, those kind of like compress on the way in and they pop into a groove. We got to pop those out. I got a little couple pictures of that. All right, here's a different design. This is a Shepa joint. Whoops, I did not mean to do that. Shepa. It looks like Rosepa, but it's pronounced Shepa. So if you look, here's your stub shaft. We've got, I forget what this is the inner race. So the stub shaft has the outer race. This is the inner race. And we have, in this case, 6 stainless steel balls, which are equally spaced by a cage. And then the CV shaft coming in. So basically this is your outer joint typically. The CV shaft coming in splines into the inner race, and then the balls right on the outer race, which becomes the stub axle that goes into the hub. Okay, so you can visualize it. This is typically an inner joint. This is typically an outer joint. This one is good because it can do some flexing, but can also do a lot of plunging in and out. And this one can turn really steep angles and still maintain that constant velocity. So it's perfect for the outer joint because the outer joint has to deal with steering and stuff. Inner joint needs to have a lot more angle. I mean, the outer joint has to have a lot more angle. So here's the Shepa, right? It looks pretty cool. You can basically see when this is at a really steep angle, look how far the ball moves. The ball is all the way on the inside, but by the top, it gets all the way to the outside. Then it comes all the way back to the inside. Then it goes all the way to the outside. So when a CV axle's at its steepest angle, that ball has got to roll all the way and all the way and all the way and all the way. Now I want to point this out because, you know, this is something I understood pretty well. When I bought my Hummer, I wanted to be able to do a lift, right? I want to be able to put some 35s, make it pretty cool. The Hummer has an independent suspension in the front, which means it uses this type of CV axle because it's 4-wheel drive. Understanding that, you know, ideally it's great if the axles are flat, right? You want axles to be flat like this. That's great. But understanding you got a Shepa joint right here. You could have the axle at an angle. The Shepa joint will compensate for that. But the steeper it is, the further the ball has to run back and forth, right? So I'm thinking about this, you know, when I bought the truck, lift kits are unobtainable. Can't even buy a lift kit. So I'm like, cool, well, I'll just lift it like with a torsion bar adjustment, but there's no way to really level the axles out because there's no diff drop kit available. So I'm thinking like, all right, I'll leave the front diff at full height, but I get the wheels down as a lift. It's going to be a steeper angle. And so I try to do some research, who makes parts, whatever. Nobody makes parts because it's just a rare truck, right? But it's mine and I love it. And it's kind of like La Toxica because I had to learn a lot of junk on my own because there's no available aftermarket stuff. They only made 1,200 of them and less than half of that are V8s. So it's just a mess. But I still kind of love it. It's a weird thing. So when I go to do this lift, I'm looking at the axles and people online are saying, oh, no, you can't go above this amount. The axle has to be flat and whatever. And I think like, you know what? I think the Shepa joint will take it. I lifted it inches above what people were claiming the max was. They're saying like, you can do like 23.5 inches from the center of the hub to the fender. That's the max. I did it like 26, like they're moving it from like 21 to 22.5, thinking they're like maxed out. I went like double that, like way over that sucker. What was the negative? My axles were at a steep angle like this. It lasts me a couple years and it's a little bit hard on the boots because the boot ends up really flexed. And so your boot is kind of like flexing as it goes. So it would kill boots. No big deal. I would pull this apart and I would boot it. If you want to replace a boot, you got to be able to take that inner joint apart and pull this boot out and grease all this up and clean it up and then slide a new boot in. So part of the lesson here is going to be on servicing this joint. if you wanted to change the joint, you could actually pull this out and pull the snap ring off and replace the joint. But I'm gonna give you a tip. A lot of these Shepa joints, they're not really designed to be serviced. So, a lot of times they heat it up and they press it together. And then if you want to get it apart, it's really tough. And so generally we don't. But you could service this boot from the inside, right? So when I got, the truck and I did the lift and it lasted me a couple years, did my own janky lift. And then I'm like, oh, the boots are leaking. I could go buy an aftermarket axle for like $100. The problem is there's no axles made for the V8 model, and there is a part number difference from the V8 to the inline 5-cylinder model. So I'm like, do I want some junk aftermarket one that has the cheaper boots? No, not really. Do I want one that's made for the 5 when I have the V8? No, not really. So what are my options? Reboot my original axles. If it were me and I was a customer and I had something nice like a Land Cruiser or something, and you were trying to sell me aftermarket axles for $100, I'm not doing it. If you break an axle out in the trail somewhere, you're done. I mean, that's going to be really tough because if a CV axle breaks, all the torque goes to the path of least resistance, which means inside that boot, the joint's just ripped apart. The other wheels aren't going to move. So I'm gonna be a hard no, hard pass. I'm not doing aftermarket trash. The OEM is tough. The problem is the boots got beat. So for a customer with something nice, I would offer a reboot. What was wrong with the vehicle? Just the boots. The boots were leaking. I didn't run it long enough to where the joint had failed. If the joint fails, this starts making noise. Clickety, clackety, clackety, clackety. At that point, you need a joint and a boot. By the time you do the joint and the boot, yeah, you're probably really going to do an axle. The new axle, though, about $500-$600. And of course, I'm looking at 2. So I'm like, no, let me just take care of these boots. So I go ahead and I boot them. Those boots last me like another 2 or 3 years. And then they started to leak. The next time, so that was like probably 5 to 6 years at running 2 inches more than what they said the max was. It's like way more. But remember, this is people on the forum. So that they're gonna, one person came up with the 22.5, and everybody else was just like parrots. They're just like repeating. I'm thinking like, nah, I'm gonna do my own thing. Right. So 5 years later, the boots are leaking again. I get ready to do the boots. When I look really closely on this housing, and I actually kept, the axles are at the school. I'm going to show you next week. Well, after SEMA. The axles on this stub shaft, which is the outer race, have blue lines right here. Blue, blue, blue. Who thinks they know why the metal is actually blue? Why would it be blue? Blue metal? Wouldn't you say that got hot? Why would it get hot?
Grease leaking out.
Right. So the grease, I overdid it the second time. I let the grease leak out a little too long. So they were a little dry. It wasn't well lubricated. So I think a combination of the loss of grease and the fact that I had it at an extreme angle, it was making the ball run all the way over here and all the way back, especially at freeway speed when it's kind of dry. And plus I'm beating on the thing. That was when I was doing the construction of this place. I was towing trailers with double the capacity of the truck. Like I was beating on it. So when I saw that there was blue lines on the races, I was like, okay, this joint, it's actually time to replace it. But kind of the point being, this joint could handle a pretty steep inclination for a pretty long time, like 5 years overloaded, beating on it. And some of that time the grease was leaking out. So it's not, you don't have to have your axles perfectly flat. They don't have to be like this. They can handle some inclination. The more you do, the more that those balls have to run back and forth, the more it's very critical that it's got grease in there. Good grease. And overall, when I did pull the grease out, the grease that was in there was like burnt. It was like caked. It wasn't really goop. If you see a CV axle slinging grease, that grease is the nastiest, goopiest, slippery grease ever. It's the dirtiest stuff. But when I pulled mine off, it was like sludge. It was like hardened up. So I definitely overheated the grease due to that extreme angle, but I don't care. It lasted me years. So like I was still great with it. I had to have those 35s. You know, I had to do it. It's like I'm addicted a little. Okay. But then when I got ready to do axles again, you know, I had to have a serious talk at home and say, hey, you know, I booted the axles. I think I might have even booted them twice. Yeah, I booted them again. I booted them one more time. So actually, it was way more than 5,000 miles. I booted them twice. So it made it like, 5 years. I think I made it like 8 years on those original axles with 2 sets of boots on them. And by then, those original axles have 185,000 miles. Like they could take it. But then I told my wife, hey, I need axles for the truck. I'm not going aftermarket. I'm going to go OEM. They're 500 a piece. I think 600 a piece actually. So am I really going to spend 1,200 in axles when I know they're going to get messed up? So that's when I really started looking once again for the lift. The main I already had it as high as I wanted it. The main purpose of the lift is rather than just cranking up the torsion bars and having the front diff high and the hubs low, the lift actually has a drop cross member. So it'll drop the diff down. But these lifts are unobtainium. They were like $7,000 when they were new and they made them for a couple of years. And then in 2009, 8, 9, Hummer was doing the bankruptcy thing. And then in 10, they discontinued the Hummer. So I have it late 09. Rancho only made the lift for a little while. Then they're like, oh, these are discontinued. Just discontinue the lift. So you couldn't get one. For me to get the lift, I had to buy a whole nother truck. So we went to SEMA last year and I bought an H3 non-truck, and I bought that truck just because it had the lift. I brought it back. I pulled the lift off of it, put the lift on mine, put my stock stuff on that one, cleaned it up and sold it. I bought a whole entire $10,000 truck just because I wanted the lift. I got most of my money back out though. The whole reason I wanted the lift was mainly so that I could get the diff dropped so my axles are riding pretty flat again. So now you're understanding the level of commitment I have to this stupid truck. There she is though. She'd be looking good. It do look good. So now you see some of the stuff that went into that. Could I have run those axles for another who knows how long? Yes. Are they making the GM axles for that anymore? No, they're not. So if I don't do the lift and I just run the axles, and let's say I get another 2-3 years and then I boot them, I get another 2-3 years and then I boot them, and then 6-7 years down the road, I can't buy new axles. I just made my truck obsolete, you know? So I get the lift. Now that the lift drops the diff, now you can see that the axle is going to be a little more straight. Does it have to do this extreme throw right here? No. So what do you think is going to happen to my axles now that they're a little flatter? They're a lot flatter, actually. They should last a lot longer. The steeper this inclination is, the harder it is on the joint, but don't underestimate it. It can take it. It could take it for a while, probably, but it's going to be flexing the boot. The boot tends to get hot. The boot tends to break down. The boot tends to leak grease. If you leak grease and you're running at that extreme angle, you're going to nuke it. Kind of makes sense. So a lot of lessons just on this stupid truck that I learned more like we would have just stopped at this page and be like, this is a shepherd joint when I went to school. I'm trying to tell you from firsthand experience, way more detail so that you know, because you're probably going to see some modified stuff. And now, you know, if you do a lift, some of the justification for the differential drop is to try to get your axles flattened back out. The negative of a diff drop though, if you drop the diff, the front differential gets dropped. Now the drive shaft going from your transfer case to your front diff is at a different angle. So if you do the diff drop, you got to make sure you have the output and the input shafts at the same angle, because remember, your front drive shaft generally is going to be a hooks joint, a U joint style. So there's a lot of stuff that goes into this. Ideally, I would buy the lift kit that has all this detail worked out. They drew it up in CAD, they ran the numbers, they did the calculations, they did some test fitting. You know what I'm saying? There's a lot that actually goes into doing a good lift, and a lot of it has to do with the CV axle and the drive shaft angles. Cool. So we'll look at the front drive shaft right here. They may call it a CV shaft, but right here they call it a drive shaft, so it's a bit confusing. They may call it a half shaft. I'm gonna call it a CV axle every time because I want you to know exactly what I'm saying, but the manufacturers may call it something different. On ASE, you'll generally know what they're talking about, right? It comes out of the front diff. This would be that inner joint. A lot of time that's that tripod plunger type joint. The main purpose of that one is to get shorter and longer. So when you go over bumps, if you're on compression, your hub is up, the distance is less. So that inner joint mostly plunges inward, right? Then when you gas it, or you come off the bump and it goes to full travel, the wheel is going to drop down. It needs to get longer. Makes sense? So similar to a drive shaft with a slip yoke, this axle needs to get longer and shorter, but how we do it is different. We have a CV joint that does all that. The CV joint will do that for us. But that's the main job of the inner joint. That's why we tend to use a tripod joint. But it can also allow a little angle too. Then it goes to the outer joint, and that's the shepherd joint. And that's the one that's like, oh, you want to steer? No problem. I got you. Oh, you want to go up and down a lot? No problem. I got you. The shepherd joint's much more flexible. It's not as good though for plunging. We need one of them that's going to plunge well, and that's the inner joint. So if you look at it, you can see in this case, the inboard is showing a shepherd, but that's a little less common. And then the outboard, actually, it doesn't really specify here. So I would say the Shepa is most likely going to be the outboard, and the tripod's most likely going to be the inboard. And they do have other types too. So we'll have a CV joint that's basically like almost like kind of like two. It's got a shaft and a ball, and then it'll have a couple of different races. They could do some different things. There's that tripod. That would be your inner joint. So we can have some different styles. They even may have a cross groove type, and these just move in their little respective races. So there's a bunch of different types, but they all kind of do the same job. So if we were to go with that tripod, this one mostly plunges. So I want to pause right there. Remember I said a lot of times a driveline vibration will depend on your accelerator pedal? There's two reasons why. Well, we'll focus on one of them, and then I'll add to it. And then I'll tell you how I learned the hard way, because I always have those. The inner joint's job is to plunge, right? So if we had a problem with this joint, and you see this one has to slide into this one, these have to move, that means these trunnions have to actually slide in kind of like a groove. Okay, so that groove was shown a little better right here. So you see that this has a little groove right here. Inside there, that trunnion has to slide on there. So in fact, we'll keep it right on this picture. If that trunnion has to slide, when would it slide? It's mostly on plunging. So if you hit the gas, it's got to expand. If you hit the brakes, it's got to contract, right? So if there was a problem in that joint, most of the time you'd experience it when you're coming from a stop and you are accelerating because your suspension's lifting up, which means the joint's trying to expand. But let's say that trunnion hits a rough spot in the race and it's like a little bit stuck. It can be stuck and it'll kind of do this, like shaking, and then it might actually break free and smooth out. But then when you let off, it might get stuck again, and then you might free it up. And then when you brake, it might go right. So you changing the throttle will induce the vibration or change the vibration or take it away. If it's a tire, you just get up to speed and it just shakes at a certain speed. You moving the throttle a little bit doesn't really change it, right? But when you're moving the throttle, that's expanding and contracting that inner joint. So the reason I know so much about that was I had a car come in. It was a Kia Sorento, actually. And it was let me think what he came in for. I think actually it was a customer pay job. He came in for a clutch. It was a manual transmission. And it had like 99,000 miles or something ridiculous, but he was the original owner, 10-year, 100,000 miles. So he came in for a clutch. I did a clutch. When I did the clutch, I was looking for ways to save time. And I had seen techs where they leave the CV axles bolted in at the hub and they undo the suspension. They swing the CV axle out of the transmission and then they just leave it dangling. So I'm like, yeah, I'm going to do it like that. That looks sick. That'll be cool. Well, when I did that, and I put the thing back in and put the clutch in, those axles, I really had to flex some stuff. They were I was pretty rough on them. I should have just unbolted the stupid things. That was something I saw other techs do, and I thought it was a good idea, so I did it, but it was a dumb idea. So when I put them back in and I go to drive the car, I notice it kind of vibrates, but the problem was when it came in, that clutch was smoked. It came in on a tow truck, so I never drove it. So I drive it and I felt the vibration. And I was like, well, it's not what it came in for, so I'm just going to let it go. Well, the guy comes to pick it up, it vibrates, he comes right back. Service manager says, hey, your car's back, it's got a vibration. I was like, did it vibrate before? And he's like, the guy says no. And I'm sort of like, I don't know. I don't really know. So the truth is, I don't know if I caused this or not, but because this occurred, I'm never going to do it like that again. In reality, I was thinking about it. I actually would have overflexed the outer joint. So I'm not sure that I did cause this, okay? Because the inner joint's the one that would more give you the vibration on Excel. But when I went and drove it, it was just as I remembered. When you accelerate, it would shake, and then you'd let off and it'd be smooth. Then you'd accelerate and it would shake, and you'd let off and it'd be smooth. And I'm like, man, this is not like a tire vibration. I think this is a driveline vibration. And in my mind, that was the first time I ever hung the axles all sloppy like that. So I was like, I think it's an axle. Now looking back though, like I'm thinking in my mind, the inner joint would cause that symptom, not really the outer. So like for real, I'm not sure I caused it, but it doesn't matter. I own it. It's my comeback. So I tell him, you know what? I think it's an axle. And the service manager says, well, it's a comeback now, so we got to pay for it. And I'm like, no, it's got 99,000 miles. It's under warranty. And so he's like, oh yeah, you're right. The axles are covered in 99,000 and 100,000 mile powertrain warranty, but a clutch isn't. A clutch is maintenance. So I said, it's good. And he said, well, which one? And this service manager he was a service advisor, gone service manager, never worked on cars, never knew, but he was fairly handy. He was actually pretty smart, but he was also a lucky duck. Like I was diagnosing a car with this dude, and I had modules not on the communication network, and I'm diagnosing a CAN network issue. And I replace one module and it comes online, and I replace another one that comes online, but only those two, and the other ones were dead. So I'm like, how did this have every module go bad? And I'm trying to figure it out. And each module is hundreds of dollars, and there's like 20. So I'm trying to troubleshoot this, and he leans over and starts playing with the antenna, and he feels it. And it's like, hey, something's up with this antenna. And he looks, he's like, this antenna is broken apart. And it hits me like a ton of bricks. Like, holy crap, this car was struck by lightning. That's what it was. The car was struck by lightning. I was diagnosing this car for like a day. And he rolls over and starts playing with the antenna and instantly figures out it's been struck by lightning. It's like, that's the type of dude he is. He thinks diagnosing the car was just playing with the antenna that he happens to find all burnt and realize it was struck by lightning. And I'm in there doing CAN diagnosis and networks and seeing what I'm saying? So this is how the dude is. So he comes and says, well, which axle is it? I tell him, I don't freaking know. And he says, well, can't you check it? And I told him, like, I don't really know how to check it. I feel the axle feels fine. It looks fine. The boots aren't leaking. And he's like, well, how do you know it's an axle then? And I said, well, it's a driveline vibration. It's going to be an axle. He's like, well, what about tires? Let's balance the tires. No, it's not like that. It's a driveline vibration. So he says, well, tell me which axle. And I say, you pick. He says, no, you pick. I say, nope, I am not going to pick because I don't know which of the two front axles it is. I have no way to verify that. He picks the left side. I put the left one in. What do you think happens? Still vibrates. And he's like, I don't think it's axles. And I told him, well, I told you, I don't know which one it was. We did the left one. Guess what we need to do? The right one now. And it's under warranty. And he's like, the DSPM is going to be all crazy saying, why'd you put two axles? Why didn't you put one? I said, well, I know that, but if you talk with the DSPM, District Service Parts Manager, and this DSPM says I didn't do a good job and that I'm not good at diagnosis, I'm going to say, well, then you find one of your FTSs and you tell your FTS to come teach me how to diagnose which axle it is. Because as far as I know, the only way to know which one it is to take it out, take it apart, and look for wear on this outer joint right here. And he kind of backed off and he said, fine. So I put the right one in, and guess what? Totally fixed it. So he was sort of like, okay, all right, you got me there. The whole point of the story was I could tell it was a driveline vibration. It made sense when I accelerated because this joint would try to plunge and it would be stuck on a little defect in this tripod in this outer race right there. But the only way to really know would be to literally take it out, take it all the way apart, clean it all out, and then look for ridges. And actually later we have one at the school. It has ridges right there. So when you'd go to accelerate, it would get stuck on the ridges and it would induce this vibration. It's pretty crazy. How do you tell which one it is? That's what I'm saying. I don't know. You got to take it apart or sell both of them. And he wouldn't go for both because it was like a warranty claim, type of thing. So I learned a ton on that piece of junk. Now you guys should know if you had a vibration that you could induce with the throttle, if it's rear wheel drive, you're thinking drive shaft, but if it's front wheel drive, you're probably more thinking like CV axle. Kind of makes sense. And then I had seen a couple since then where this inner joint was actually loose. Like you could move it and it was like, oh, that's loose. That's definitely the problem. But this one, I couldn't feel anything. Right. So it was a really cool diagnosis. Now let's talk about this outer joint. When do you think you'd hear we're going to go from vibration to noises? Because generally the inner one is a plunging issue that would cause more of a vibration potentially. If this joint was bad, when do you think you would experience something and what would you experience if it's the outer joint? Anybody got an idea? Like, let's say, how about this? Let's say this is from the top down, not from the front looking front to back, but if this is the top down, this is your inner part of your axle, this is your outer. What's happening right here in this condition if it's from the top down? And this is the right side axle. That's like a hard left turn. Would you agree? That's a hard left turn. And on the hardest of left turns, the ball has to go all the way from the inside to the outside. So if you have some defect on the very outer edge of the inner race, you're not going to experience it going straight. You're only going to experience it when you do a turn. So if it's an outer joint, the main thing you'll experience is a clackety, clackety, clackety on turns. If you're going straight, the ball just sits in the center. If you're turning, the ball's got to go over there and get into the defect, and it's clack, 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 and then you straighten it out. So if ASE asks about, a vehicle makes a cracking, slapping, clunking noise while you're turning and moving, it'd be like probably a CV joint. Black, 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 black. What would you do if it was a customer car? Lift it up, inspect the boot. If the boot's torn and the grease has come out and it's making noise, it's too late for a boot. The CV joint's damaged. You could sell them a CV joint in a boot, but that doesn't really make sense. You're just going to do an axle. If you want to do an aftermarket axle, cool. But if you're a legitimate repair shop, you have to warranty that. Depending on how long you're trying to warranty it, it may or may not last. Some of those cheap axles are pretty junky. I've also seen issues with the splines on the cheap axles where they don't fit real tight to the hub. And then ever since you put an aftermarket CV axle in, when you go from park to reverse, there's like a clunk right there at the hub by the rotor. Yeah, they're not a perfectly machined spline. So I really try to stay OEM if I can, generally for everything, but especially for axles. All right, so that was kind of overviewing like we were talking about. There's that couple types of different joints. You guys should be pretty decent on this, on the failures and stuff. Now there's one thing that we're going to talk about right here. It's called torque steer. Think about your extension. If you're trying to take a bolt out and you're using this long extension, you might use your impact gun and have it go brrr, and it might not loosen up the bolt. What would you do to get the bolt loose with the same impact gun? Use a shorter extension. The longer the extension is, the more the metal flexes and it kills the torque. In fact, this same principle applies for torque sticks. So this thick torque stick, this old thick boy here, is a 140. And this one that's thinner, doesn't look thinner, is a 100. I've actually got a really nice one. This thick boy and this little thin one. In fact, let's just go for the thinnest. See the difference? This one is going to transmit a lot more torque. This one's going to be a lot less. This one is like a 55 foot-pounds. So this is going to kill your impact on torque because it's so thin and this metal's going to flex, right? So it's the same type of an idea, except with axles, you don't have a thickness difference. What you have is a length difference, right? So the longer it is, the more this is going to flex. So on the one side, because remember the engine's on one side, the transaxle's on the other. So it's got a short axle and a long axle. On the long axle, more of the torque would be decreased. So if the torque was decreased on, let's say, let's go with the torque is decreased on the left side because it has the long axle, and the torque is higher on the right side because the short axle. When you went to accelerate, the front wheel would pull harder and the left wheel would pull a little less, and that would rip the steering wheel to the left. So you'd accelerate and it would do torque steer to the left. So what we do to minimize that is we put a big, thick, fat intermediate shaft in between, and then we end up with the exact same axles left to right. That's the whole purpose of this intermediate shaft. That's why you have the axle bracket stuff we were doing with engines. So that's the reason that we have that. It's not a real big deal. There's one more thing I'd like to point out. If you were to accelerate and have it cause a pull, that might be because, let's just say, you look at your transmission. If your engine mount is no good, your engine can lift up more and that would extend the axle more. And that could cause two things, maybe a pull, but also if you think about it, remember that plunger joint? If you're accelerating and it really has to expand a lot, that could actually cause some sort of a vibration, because especially if it was, something more to do with like a hooks joint, a CV axle, a hooks joint, a U joint, your angles can change, especially if it's got an engine mount over here and a transmission mount over here. When you accelerate, it might actually lift up a lot and induce a vibration in the axle. So your CV axles start to kind of roll over towards powertrain mounts. Your powertrain mounts should hold them in a specific location. If your powertrain mounts are bad, you got your engine, your transaxle moving around, that's changing the distances of the axles, which can cause torque steer, but it could also cause like a vibration, for example. Kind of makes sense, especially when you get into like, if you had a vibration in drive, but not reverse, right? Because remember, we talked about that a little bit. In drive, the engine's kind of pushing down, but in reverse, the engine's kind of pushing up, or the other way around. I think it's the other way. Acceleration is like this, reverse is like this. If your engine or transmission mounts are worn, your engine's able to move more. It's messing with your drive shaft angles, but it'll change your drive shaft angles in reverse, or in drive, it would be kind of opposite. So if you ever have a concern that's a vibration in reverse but not drive, or drive but not reverse, that's all got to do with your engine and transaxle position. Okay, be thinking engine or transmission mount. Cool. Similar to torque steer, but A2 and A3 aren't asking you about steer. But A4 may have asked about steer, and that's why it could be an engine mount or a powertrain mount. Cool. Now, more about CV axles. They can have this. What the heck is that thing? That's a reluctor for ABS. So if you put a CV axle in that doesn't have this, you're going to get a wheel speed sensor performance code. You're going to get ABS light on because it needs to have that on there. Cool. And then here's looking at a boot. You can have different types of boots. This is a split boot. This is like a temporary repair. This is not really a good repair. If you want to replace a boot, you need to take the axle out and disassemble the joints and slide the axle in and repack grease in there and reclamp it. And by the way, there are special tools to do those clamps, which I generally keep. Although I haven't used them in a while, I did use them fairly recently. I'm going to show them to you because it's pretty rare. But there are specific clamps. I know where they're at. They're in this drawer. Okay. This is to clamp those boots. So if you want to do boots, you're going to need pliers like this, but you don't squeeze them like this. Look what it's got. It's so you can put a torque wrench on one and a breaker bar on the other, and you can actually achieve a certain torque to really clamp those. You don't just get to put a janky basic hose clamp on. Part of the reason they're so specific on those clamps, this gets a ton of centrifugal force. It spins really fast, so the grease pushes really hard, and it really tries to leak out. If you have a pinhole because you were working on it and you nicked it with a pick, or your socket rubbed through and you're trying to get hub bolts out or something, if you have any tiny leak, that grease is going to be pushed so hard at highway speed that grease is coming out. It's going to be slung on the control arm. It's going to be slung in the fender liner. There's going to be grease everywhere. So when we seal these, we need to do a very good job, or it will leak. Kind of understand? That's why this is a temporary repair. This is a piece of junk. No, not going to do that. In fact, I wouldn't even use an aftermarket boot. I like the OEM hard plastic, thermoplastic boots. Nice. These gummy silicone ones, nah, junk. Too soft. All the aftermarket ones come with these cheap boots. I like OEM, especially for the outer joint. They have the hard thermoplastic. Cool. For that, probably pretty good. If you actually break a CV joint, again, the vehicle won't move. All the torque will go to that CV joint, and it just will freewheel inside the boot. So if you ever had a car and you thought it was a transmission issue, and you were to actually turn one of the axles and notice the axle turns, but the inner part of the CV axle doesn't, they move independently. No, those need to be one piece. If it's broken apart like that, you'll think it's a transmission or a differential. You could totally misdiagnose that, when in fact it could actually be the CV joint broken. If it breaks and it comes apart, you can see it. But if it breaks and it stays inside the boot, you'd be surprised. It can fool you. I had a couple cars I've had to diagnose, and the people thought it needed a transmission and it needed $100 axle because they're kind of junky, so I didn't go OEM. All right, and then inspecting them, looking for cracks. If grease starts to come out, we need to catch that right away. Again, if we're going to drive it, we're going to feel for vibration. If it's the inner joint, we're going to generally listen for noise on turns. If it's the outer, right? Clackety, clackety, clack. Look at the boot for leaks, cracks, etc. Check the clamps. Now you can see that clamp. See how that clamp was squeeze special? Now you can see that what that tool actually does. This one, for example, the boot is ripped, but also you see a lot of road debris and grime. No, I wouldn't reboot that. That once dirt gets in there, it's going to damage the joint. The joint's damaged at that point. It doesn't make sense to just boot it and grease it. Cool. Checking it, feeling for looseness. Like I was saying on that Sportage with the vibration, I didn't feel any looseness. The axles felt fine. There was some minor defect inside, just that little wear on the inner joint race. Okay, and then when we go to do some of this work, it requires a special type of lubricant. So right here, we're about to slide this boot off. This one actually is broken, but when we go to do a boot, you have to get the grease too. It comes with a very specific type of grease, and that generally comes with the boot kit. Also, the CV axle has the axle seal in the transaxle. We'd want to inspect that axle seal. If the axle seal's leaking, it kind of makes sense to do them all at once. But the other thing is that axle seal could leak because of damage on the axle shaft. It's the same like a rotating surface, which has to be clean. If it's scored or rusted, it's not going to work. Now, to go and do the job, here's a couple tips. When we go to do ball joints, remember, you can bang on it with a hammer and peen the threads over, or you can do what I showed you at the pry bar, or even better yet, you can use a puller. So this is a ball joint separator. It's really just a 2-jaw puller. That'd be a good way to do it. Additionally, when you go to drive the axle out, first off, if it's a staked axle, you need to unstake it well, and definitely spray some lubricant here, because that axle nut coming off can make a lot of heat and it can gall, and then you'll ruin that $500-600 axle and the nut, right? So there's a whole lesson on that. But additionally, when you go to drive it out of the hub, don't bang on it with a hammer, because you'll peen the threads over, and then it's kind of mushroomed, and then you can't get the nut to go, and then you got to try to file it, whatever, and maybe even replace an axle. I would use an air hammer, go right in the middle, because it's got a little point, and that'll hold the air hammer and just drive it out. And then pull it out from the backside. And then on the inner side, you see this pry bar. A lot of times you can use a pry bar, and it's not about prying hard. It's about like popping it loose real quick. pop, it'll come out. If it doesn't, this is actually a great tool. This is a slide hammer with like almost like a fork on it, and you get behind it and you bang the slide hammer outward and that'll pop it out. Now, this is all about that little circlip we saw in that picture. That little circlip is in there. When you slide it in, it contracts. Then when it gets into the groove in the side gear of the differential, it goes pop. So when we're pulling on it, we're really just trying to get that clip to kind of pop out. Now, when you go to install it, you're gonna press on it. And when it goes to pop back in, you'll know. It's not like you just push it in. You're like, you should push on it and have to go like this. And it will go click. And that's how you know the circlip is actually in its groove. So you definitely want to do it like that. Okay, and then here, if we're going to do the boot, you can see we put it in a vise, and the vise has like soft, it has jaw protectors, soft grip. Cut the clamp, take it out, clean the grease out. It's all sorts of nasty. Here's popping the snap ring out, pulling the joint off, inspecting the splines, checking the trunnions if it's the inner joint, checking all that out. And then if we're going to do the new boot, get the boot on there, pump it full of new grease, get a new clamp using those special pliers. And a lot of times there will be a torque spec, right? So we're going to do this this rebooting procedure, but this is just to get you warmed up on that. And then additionally, and the snap ring, that the retaining ring that goes into the differential, lube that up. In this case, if it's an automatic transmission, the petroleum jelly is good. If it's a manual, you might use a little bit of like petroleum-based grease because that's going to kind of mix in with the gear oil or whatever it uses, depends on the transmission. But it's a good idea to lube that up, not go totally dry. Then why do you think we're lubricating this point? Because this rides in the differential side gear, but this, oh, that's where the axle seal rides. So this is what we need to inspect if we have a leaking axle seal. And then lubing it up is going to help prolong the lip of that seal. Makes sense? What lube? Depends on the transmission. This one's automatic, so that automatic assembly lube is perfect. And then here we go, slide it in like I was saying, and make sure, again, you compress it. You could even do it like this. This will basically like work as sort of like a pogo stick. You hit the end of it. This outer stub shaft hits the inner shaft, and the inner shaft transfers that to the other stub shaft and then pops it in. Cool. Then when you go to put it in the hub, it's a really good idea to lube these splines. Anti-seize is fine because it's metal on metal. Just don't use anti-seize on anything with rubber. But that would be fine. This is especially important in the rusty areas because if you take the axle out and you don't lube it, and then somebody has to do it years later and it's seized in the hub, it can be a nightmare. It can be a total disaster. And it'd be really fun if it was you. If you did like not a real good job on the first time, and then you're the one who has to get it out, sucker. And then there it is, just sliding it in and then torquing the nut to spec. And you guys have made it. Okay, so now if you got any questions, I will take your questions.